The following message is best viewed on an oscilloscope.
Okay, good morning. Welcome to this first morning session of the Detectors for Future Facilities R&D Novel Techniques. It's the last session of this program block, and my name is Michal Marčovský. I'll be the chair for the first part of the session, and after coffee break, Bitesh Patil will take over. So altogether, we'll have to today 18 presentations. The rules are simple. Please mute when you are not speaking. The presentations should be long 12 minutes, after which you will get 3 minutes for discussion. And I will remind you after 10 minutes of your talk that you get a 2-minute warning. And if any of you participants have questions, please raise hand in this participants window, and please do have questions. So I believe we can start. And the first speaker is the Tomohiko Tanabe from CLIC, and he'll be talking about ILD. So please go on.
Hello, it's Tomohiko. Can you see my screen?
Yes, we do.
Okay, so it is a pleasure to talk about ILD, a detector for the International Linear Collider. The ILC is a proposed electron-positron linear collider. It will start as a Higgs factor at 250 GeV. The proposed candidate site is in the northeast region of Japan. Here, it can house an underground tunnel of 50 kilometers in length, and that would correspond to a future upgrade of 1 TeV and possibly beyond, depending on the technology available at the time. So such energy extendability is a unique advantage of a linear collider. And another advantage of a linear collider is the polarized beams. And there was a dedicated talk by Jenny yesterday, so I refer you to her slides. And the physics goals at the LC are precise measurements of the Higgs boson and electroweak observables. At 350 GeV and above, the top pair production opens. And at all energies, we search for new physics, new particles beyond the standard model. So in terms of the project progress, last year in March, the Japanese government expressed interest in the LC project. More recently, in June this year, the European Strategy for Particle Physics mentions ILC explicitly. And furthermore, there is support from the United States expressed. So there's global support for the LC project. So all of these factors have resulted into a new development for the ILC. Here I show the proposed timeline. The ILC International Development Team is expected to start taking over from LCC and LCB Linear Collider Collaboration Linear Collider Board structure, taking over from this organization, and then it will start as soon as next week for a period of up to 1.5 years, followed by 4 years of pre-lab or preparatory laboratory. And after a full project approval, if there's a full green light, then the construction can start. So in terms of the detector design, we should be ready around the start of the LC laboratory. So this will give us about 5 years of time. ILD stands for International Large Detector. The ILD concept group currently consists of 64 institutes from 30 countries around the world. ILD has recently published the interim design report in March this year. So this is the most recent comprehensive document. And if you want to learn more about ILD. ILD is a general purpose 4-pi detector, in many ways typical of a collider experiment. But I should note that the we use the time projection chamber, or TPC, for the main tracking device. And all the tracking and all the calorimeters are placed inside the magnet. This is to ensure there's as little material as possible before the particles reach the calorimeters. So in terms of the design goals for the detector, it is important to note the special features of the LHC, especially compared to the LHC. There is much lower backgrounds, much lower radiation, and very low collision rate. So all these things allow us to pursue relatively more aggressive detector designs. I list here some of the detector requirements, along with the relevant physics goals. So for the impact parameter, resolution is important to perform B tagging, but at ILC we can also perform charm tagging. The momentum resolution is important to perform the Higgs recoil study, where we reconstruct the leptonic Z decays, and the Higgs mass can be reconstructed without looking at the Higgs decay, since we know the initial state. The jet energy resolution should be around 3 to 4% at high jet energies. And the hermeticity, or the polar angle coverage, should be down to around 5 milliradians. So all these requirement numbers are around a factor 2 to 10 better than a typical LHC detector, but we of course benefit from the nice features of the LHC environment. ILD is optimized around particle flow based on the highly granular calorimeters, low mass trackers, and software reconstruction. And this allows us to separate the clusters at the particle level, as shown here. So the bunch structure of the LHC has some many impacts on the detector design. When we look at the bunch train, its length is about 1 millisecond. But the interval between two bunch trains is 200 milliseconds. So there's a lot of time where there's not much going on collision-wise. So this immediately suggests that we could turn off the detector during this time, or the so-called power pulsing of the subdetectors with a duty cycle of around a few percent. This power pulsing is being studied for essentially all the subdetectors, but for example, for the Vertex detector, the power consumption is expected to be reduced by a factor of around 20. There are many other implications for the readout and cooling strategies. Less power means less cooling needed, and therefore less associated material. More time for the readout between the bunches means that we can perform triggerless readout and perhaps even per bunch offline processing. So I will now talk about some of the subdetectors, starting with the tracking and then the calorimeter. So first, the Vertex detector, which is evidently the final subdetector to be installed. And its R&D is expected to continue well until 2030. So the current design is the 3 double layers with the innermost radius of 16 millimeters. Its main challenges are to cope with the beam backgrounds, reduce power consumption, and make the material budget as low as possible, 0.2 to 0.3% radiation length per layer. The technology options are CMOS pixels, fine pixel CCD, and depth. In the case of the CMOS pixel, the Bloom collaboration has made a prototype whose material budget is around 0.3%, close to 0.3% the requirement. So this is nice. The CMOS sensor has also been successfully used in the Bell 2 beam commissioning a few years back. And of course, the depth is used as a Vertex detector for Bell 2. Some of the parameters still need to be improved for the final design goals for the ILC or ILD, but we are well on our way here. ILD uses the time projection chamber, TPC, as a central tracker. Here, the ionized electrons caused from the charged tracks drift towards the anode end plate, and the drift time of the electron can be converted into the longitudinal position. This allows us to give us three-dimensional, essentially continuous tracking, like shown here. It's a gas detector, which means it's naturally low material budget. We can measure energy loss dx and perform particle ID. More on this on the next page. The readout options are gem, micromegas, and pixel. And one thing to note to take care of in the TPC is the ion backflow coming from the amplification. And if left unmitigated, it will distort the field and will cause bad things for the electrons drifting. What we do with the ILD is to install gating devices and collect the positive ions in between the bunch trains. So evidently here we again take advantage of the LC bunch structure. You see here some pictures of the TPC test module and test beam data. More words on the particle identification. In the left, I show the DDX simulation plots expected from the TPC and the expected separation power comparing pions versus kaons and kaons versus protons. And naturally, there are blind spots where the curves overlap. One way to improve this is to make use of the time of flight information. Here we assume ecal first 10 layers, so providing 100 picoseconds of time resolution. But please note this is still a proof of concept, as the number needs to be demonstrated in test beam prototype. But this shows a nice prospect that combining both DDX and time of flight gives us a coverage also in the DDX blind spots, and gives us separation power across the momentum spectrum. So particle ID offer unique physics opportunities, and here as an example, I show the forward-backward asymmetry measurement for PP-bar pairs. Here the Vertex charge reconstruction is corrected using KOID, and the detector acceptance is also corrected. So in this angular distribution, the corrected distribution very closely resembles the generator level distribution shown in green here, which is very nice. And more on this can be found in the talk given by Adrian in the top Lecture Week session.
Tomohiko, 2 minutes remaining.
Thank you. For the ECal and the HCal, there are dedicated talks. I will be brief here. So for the ECal, the active layer sense technologies are silicon tiles of 5 by 5 millimeters square, or scintillator strips of 5 by 45 millimeters square. Both use the tungsten as the absorber for making the showers compact. I would say the ECal is an ultra granular calorimeter with the number of readout channels reaching up to 100 million. For the HCal, the active layer technology is either scintillator tiles of 3 by 3 centimeters square or gas RPC 1 by 1 centimeter, both with using steel absorber. So a few words on the forward calorimeters. From the center of the detector toward the outside, we have the LumiCal, the LHeC, and the BeamCal. And I believe we have a dedicated talk on the LumiCal later in this session. Here I show some simulation and reconstruction plots for the BeamCal. The energy deposit is integrated here, and you can identify an electron like this. So altogether, the calorimetric hermeticity is down to 6 milliradians. And this hermeticity is especially important when performing BSM searches, which often typically involve missing momentum. So processes like BABA's scattering, E-gamma and gamma-gamma processes can be major backgrounds if we missed the scattered electrons. So one example is I give here is the monophoton WIMP search. Here, around 6 milliradians is a nominal coverage, but if the hermeticity is made worse, let's say around 15 milliradians, then the number of BABA backgrounds would increase tenfold. So every coverage, milliradian coverage counts for this kinds of background rejection. So now I'd like to summarize my talk. The LHeC is a proposed Higgs factory with energy extendability of 1 TeV and possibly beyond. ILD is optimized around particle flow with highly granular calorimeters, low mass trackers, and software reconstruction. There have been lots of efforts made for the detector R&D, but still there are many opportunities and open questions, such as we need more detailed design of many subdetectors, especially the additional silicon tracking detectors. We need to demonstrate the use of timing information. We should probably need more work on the calibration alignment. It's always nice to have better reconstruction software and physics studies. And since we still haven't decided on our technologies, there's potentially room for new technologies. So ILD welcomes new people and new ideas, and we hope many of you will join us in the future. Thank you very much.
Thank you, Tomohiko. Now, are there any questions? I don't see any hands raised, so I will ask a quick question. This time of flight with incl with 100 picosecond time resolution is quite challenging. Can you comment on that? How are you going to reach it?
This I will have to defer to an incl expert who may be able, if they're able to help me here.
Yes, I can answer a bit on this. The chip already has 1.5 nanosecond resolution. This has been measured on test beam, and by combining the different layers, we can probably reach something which is not that far already. But there are still some developments to be done to achieve this and prove actually that we can achieve this globally.
Okay, thank you very much. So it's a work in progress. Okay, so I think Tomohiko again, and now let's continue with Yuji Yamazaki from Kobe University with the talk on the updated LHeC detector.
Okay, do you see my slides?
Yes. Yeah.
Okay. Okay, then let me start. My name is Yuji Yamazaki from Kobe University. I'm going to talk on behalf of the LHeC study group on the updated LHeC detector. Just a moment. So the scope of my talk is the following. We have published the CDR for LHeC some time ago with very much detailed studies. And in addition, we had one section in FCC CDR on FCC-hh detector. Recently, we have updated these. Indeed, this was published just the day before yesterday. And this was motivated by the fact that we have optimized the accelerator design from, we have reduced electron beam energy, but with high luminosity. We have physics updated thanks to this high luminosity, for example, like Higgs. And then meanwhile, we have also technological advancement. And we would like to also see some variation in our design. So my talk will be after some introduction of the high energy PA collisions. I will cover with detector update like the listed here. Okay. So this is the picture of the LHeC and FCC-hh. For both, electrons are accelerated using dedicated energy recovery lineup. So we have 3 turns here to reach the beam to something like 50 or 60 GeV to let it collide with other, the proton or heavy ion beam. For LHeC case, the hadron beam are the same as LHeC, while the electron energy is 50 GeV, and this achieves beyond 1 TeV center of mass energy with this very high luminosity. For the FCC, the electron energy is not much increased, but proton energy is very much higher, and this reaches up to something like 3.5 TeV of center of mass energy, which is something like 10 times higher than our previous EP experiment, which is HERA. So let me talk a little bit about the processes and challenges at the LHeC and the FCC-hh option. So our main process is neutral current events, as illustrated here in event display. This is the scattered jet, the parton fragmented in jet, and this is the scattered electron. The proton comes in this direction, electron is in this direction. We need to tag, of course, the scattered electron in wide angle from lowest Q-square event to highest Q-square, and we need to also look at the hadrons, which tend to be go in what we call forward direction, the outgoing hadron direction. And there we would like to have our as good as possible flavor tagging for measuring the parton density functions flavor dependence. Then we have other process, which is charge current. And there, of course, we would like to measure missing PT in order to tag the neutrinos. And we also would like to measure the reconstruction of kinematics, including this hadron jet direction. So indeed, we measure both longitudinal and the transverse momentum of the jets. And of course, the another important physics at the LHeC is the Higgs production through these charge current events. Indeed, by W boson fusion, we have copious production of Higgs, and there the primary channel we would like to focus is this CC bar, because this can be measured possibly for the first time among all the colliders. And Higgs boson indeed flies pretty forward in the CP collisions, and we would like to have best flavor tagging ability again in the forward direction. And of course, jet resolution should be as good as possible to reconstruct the hadronic decayed Higgs mass. And with these requirements, together with these all the physics aims, we would like to build LHCC detector with fulfilling these requirements. So this is an illustration or the drawing of the LHCC detector. Our design is based on LHC experience and a high LHC upgrade, but the big difference is that the radiation is much lower, like 1/10,000, and there would be almost no pileup. So the technology developed for somewhere else, like the ILC technologies, about which we have just heard, may also be applicable. We also would like to have, of course, very hermetic detector, but at the same time, a modular one, because we need to install the detector in the interaction point 2 during the 2-year shutdown, because it is currently used for the LHeC experiment. So this is let me start with the interaction point and magnet of the LHCC. So this, on the right bottom corner, you see the interaction point drawing. And there is a beam 1 from LHC, which is not collided, and proton beam 2 is collided with EIL electrons. You see that it is a head-on collision, and this S-curve bending is provided by a dedicated dipole magnet, which is indeed inside the detector, but outside our detector solenoid. So it's a big one, providing something like 0.21 Tesla with opposite polarity here and here, before and after the collision. And this is the synchrotron radiation simulation. And you see that thanks to this design, this radiation is actually not too wide, and we have not too much beam element around, so that we have a good acceptance to our detectors. The main update on this CDR update is the central tracker. So this is the 3D view of the tracker. You see that the beam pipe has a funny elliptic shape, and this is because of to house the synchrotron radiation, around which we have a 1 pixel layer, and around there we have cylindrical layers. We would like to use low material tracker by DMAPS or CMOS sensor technology, which has a benefit of combining readout electronics integrated in the same wafer, so that we have a very thin detector. And at the same time, it is very rather hard. And indeed, for the LHeC, the current level is good enough for standing for the high-LUMI operation of the LHeC. Also, this allows us to put these detectors in very forward, very backward. We have something like 5 to 8 layers for this wide range of rapidity coverage. And if we look at the material budget as a function of rapidity, you see that for the entire coverage, there are very little material, like something like 0.5 x zeros, and this allows us to measure the tracks at very low momentum, 100 MeV, with something like 1 to 3%, and at the same time, the impact parameter resolution for 1 GB track would be something like 100 microns, and it's much better for the higher momentum. We have still room to improve. One is to put second pixel layer, and another is that the beam pipe could be thinner because if we have more detailed simulation of the synchronous radiation, maybe the beam pipe can be with smaller diameter in the backward direction. Backward means the electron injection direction. As for the calorimeter, our baseline is liquid argon housed inside the cryostat for the solenoid. And for the forward region, this consists of fine segmented plug calorimeter thanks to the technology developed for the ILC. What we investigated this time was a warm option for the liquid argon calorimeter because instead of liquid argon calorimeter with scintillator and lead, and because this has more modular design, and according to the simulation, this performs almost equally well, but again, we see that liquid argon performance is actually quite good. This has a still benefit of radiation stability and segmentation. So we are going to see, compare these two technologies, and it's good that there are some flexibilities. Okay, so for the muon system, our design is we have no dedicated magnet as a baseline design, but instead we have return yoke, and in between we have 3 stations of muons. So the ability required for the muon detector is mainly for very good tagging and fast trigger. For that, the technology from HL-LHC, like very thin RPC with very good timing, and drift tube with smaller diameter, small diameter of 1.5 centimeter would serve very well. This was developed for the Atlas Phase 1 RPC-MDT, which is about to be installed. It turns out that this has very good performance, even possibly maybe we don't need this good detector we are going to see. Anyway, we are also thinking about the possible extensions, in particular in the forward-backward direction, because there are muons, for example, from the JSI decay can be tagged, and then there we can do some good physics. So around 0 degrees, since we have IP design, we can think concretely of the beam related to detectors. For example, the forward photon spectrometer can be placed, of course, using very similar design to the LHC. But another thing is that we can put also 0 degree calorimeter, indeed possibly much bigger one than what is in the LHC, because we seem to have big space available thanks to this large separation of the beam 1 and beam 2, and the aperture is also quite a large one available. So the technology candidate to measure this with the neutrons mainly by this 0 degree calorimeter is silicon tungsten, because we need very good position resolution, but at the same time it has to stand for something like order of 10 megagrays, and we at the moment it is pretty tough to do with silicon, but we hope that we have further technological advancement meanwhile before we realize this we install this detector such that we can use silicon. So this last item is the detector design for the FCC-hh. The big difference from the LHeC is that proton energy is 20 or 50 GeV against 70 GeV, while the electron energy is basically very similar. So what we need to do is to absorb the forward-going hadrons by having thick HL in the forward direction here, while for the backward, the detector is not much changed. We of course would like to have a good resolution tracker, so for that we would like to have a very long cylinder of this wheel-like structure of the tracker. And by having such kind of detector, it turned out that it is performs good enough for also for very high energy collision of FCC environment. So let me summarize. We have successfully designed a new generation EPEA detector for high precision QCD studies, Higgs, top, and BSM physics. And what are very much different from our previous detector, HERA, is that we have much wider acceptance, in particular for the tracking, thanks to the modern technology of silicon detectors. And the current design achieves this performance goal also for the FCC-hh, and further optimization is ongoing. Okay, thank you for your attention.
Thank you, Yuji. Now, are there any questions? I don't see any questions. I will ask a quick one.
Yes.
Can you comment on these macropixel detectors? What is the expected technology?
I think we use also the CMOS sensor, the same one.
CMOS. Yeah, so it will have a much larger pixels.
Right, right.
And larger capacity.
I mean, we have fine pixel, and then for the next 3 layers, it seems like that this larger pixel would have enough performance.
So they are just a slightly larger pixels. Okay.
Right.
Thank you. I see no other questions. So thank you, Yuji. And let's continue with Franco Bedeschi from Infinite Pizza from a detector concept for a circular E plus E minus collider.
Did you get to the full screen? No.
No.
Okay. Now you should.
Yes, that is perfect.
Have it.
Yeah.
Okay. Okay. So let's go. So I'm going to describe you a detector concept proposal that has been developed explicitly for the future circular E plus E minus colliders. And the reason for that was that since the beginning, when we started looking at the physics at circular E plus E minus colliders, we realized that the situation was rather different from the situation at the linear E plus E minus colliders. So you could not just simply extrapolate the detectors that have been developed for linear colliders directly into circular collider. So the reasons have been partly described by the first speaker of this session, but there are also others. For instance, the solenoid detector solenoid field cannot be too large because otherwise you blow up the vertical emittance of the beams. So you have to keep it rather small. In fact, at FCC-hh, it is optimized around 2 Tesla. So you have to compensate with a larger tracking volume, and that forces you to put the calorimeter outside, and therefore you want a very thin coil. The other point is that the beam time structure, as was pointed out by the first speaker, is very different. In fact, in circular collider, you have a bunch structure which is fairly similar to that of LHeC, at least at the Z pole, with larger spacing as you increase the energy. But certainly you don't have a larger time gap, so you cannot do power pulsing, and cooling become an issue for particle flow calorimeters and Vertex detectors. Also, TPC has troubles in this environment. So this is what we have come up with. We called it IDEA, which stands for Innovative Detector for E plus E minus Accelerator. And this detector is described in detail in both of the CDR of FCC-hh and CEPC. Okay, so more in detail, this is the cross section. You start with the Vertex, high precision Vertex detector, followed by a large drift chamber based on helium gas. Then you have a silicon wrapper to boost the momentum resolution, and a thin solenoid, followed by a dual readout calorimeter, which is 8 lambda deep, and an instrumented yoke with muon chambers. Now, since the magnet is small, also the yoke is small. In fact, you need only 1 meter of iron in order to constrain the magnetic field. For the acceptance, the tracking goes to 150 millirads because we don't want any material in front of the luminometer. And the calorimeter goes to 100 millirad, which is as much as you can go without interfering with the quadruples of the final focus. The other point that is specific to circular collider is the fact that the energy is naturally limited. So the typical track energies are relatively small, certainly always below 100 GeV. This is examples of the muon distributions in ZH associated production. And therefore, transparency becomes more relevant than the asymptotic resolution of your tracking system. On the left, you see the material that is a very light detector. And on the right, you see the momentum resolution as a function of PT. This is the blue continuous line. The red line is a comparison with a detector based on full silicon tracking, extrapolated from a detector of CLIC. And you see that even if the asymptotic resolution is better with the full silicon tracker, then, however, the multiple scattering is really hurting you in the area of interest. The transparency is very important also for the Vertex detector, because you would like to make it very transparent and therefore go to air cooling. So that means less than about 20 milliwatt per centimeter. For the resolution, well, we have been shown by previous experiments that you can reach 5 microns with 30 micron pixels. So we aim at 20 micron pixels for a 3 micron point resolution, same as the ILD. With that and our geometry, the asymptotic resolution on impact parameters in the transverse and longitudinal plane is about 2 microns, which gets degraded by multiple scattering to about 15 microns around 1 GeV. The drift chamber has a readout that including the counting of the ionization clusters generated in the drift cell. This is very important because it boosts the particle ID resolution. In fact, you see, for instance, the K over pi separation in the blue lines that are in the plot. The dashed lines is what you get with the standard EDX, and the continuous line is what you would get, you expect to get with cluster counting. So this gives you XL more than 3 sigma K pi separation over the whole momentum range, except for a very small region around 1 GeV. Of course, you could recover that with a timing layer, but you don't need a very extreme timing, 100 picosecond resolution to do the job. Okay, for the calorimeter, you need a good but not extreme electromagnetic resolution in the order of 10% of √V, sufficient for Higgs physics. You want to do very good instead on jet resolution because you want to clearly identify hadronic WZ and H decays into 2 jets. You would like a good transverse granularity, possibly less than a centimeter for pi0 reconstructions for tau physics. And also you would like to have all of the electronics in the back to simplify all of the cooling services. Now, we think that dual readout calorimetry satisfies all of these requirements, and you get an electromagnetic and hadronic calorimeter in the same package. I have no time to discuss it. I put here some references that you can look at that. But let me tell you something about the estimated performance. We did a full GN4 simulation of the 4-pi detector that was tuned, however, to the test beam data collected by the RD52 collaboration. And the electromagnetic resolution average over 8 and 5 is indeed around 10%, 11% plus a small constant term. And we also showed with the simulation that dual readout works very well with jets. And in fact, if you look at the separation between invariant mass to jet invariant mass distribution for W, Z, and H, you see that they are pretty well separated as shown here. We are discussing with some American collaborators also the possibility of a crystal option to be placed inside the solenoid. That would give an extremely good 3% to the square root of E for the electromagnetic part. And we are also considering the possibility of a timing layer in front based on LISO tires that would give you 20-30 picosecond resolution. A glimpse to the R&D that we are doing, as there is a lot of work going on maps for the Vertex detector using CMOS technology. This has been described by a dedicated talk yesterday on the Arcadia project. For the outer silicon, we are thinking about CMOS passive strips, long pixels. In general, this is all evolution of the R&D for HL-LHC. For the drift chamber, we are exploring light mechanics and new wire technologies, for instance, the carbon fiber wires. And of course, we are developing cluster counting electronics to be directly on detector. For the calorimeter, scalable mechanical options are important. For instance, we are now making prototypes with brass capillaries that get glued together and to make a calorimeter modules are you see in these pictures. And also we are looking also at ways to read out a very large number of silicon PMs, which are the sensitive medium. So we are studying architectures. This shown here is the first system which is being developed at Kane. And also several possible readout chips to be implemented in these boards. We are also looking into the possibility of digital silicon PMs.
2 minutes.
Of course, there are also crystals to be studied, and this is also going on. For the muon chambers, we are working on a technology called micro Arwell, which has shown to be very suitable for industrial production, and we are working with several industries to push this forward. Okay, this is my last slide. So in summary, detector consists of a high precision vertex detector. It has a high transparency and good momentum resolution. Has a good integrated particle ID using cluster counting, and even better with the timing layer. Has an excellent calorimetry that becomes really fantastic if you add the crystals. Has a light solenoid and a very minimal yoke. A tracking muon system, and delivers excellent performance at all energies at the Z, at the WW, ZH, and TT. So this, however, is based all on achievable technologies. However, there is still need of R&D and software simulation. We need to finalize all of this, optimize, reduce cost, and engineer the full detector. So much R&D work is in progress already, has started actually a few years ago, supported by several funding sources. However, excuse me just a moment. Collaboration on all of these R&Ds is really growing internationally, but there is still ample space for additional contributions. So to conclude, I think we should do it, and of course we need a lot of young people to do it.
Okay, thank you very much for your nice talk about the idea concept. So are there any questions? Yes, I see Jenny.
Yes, thanks for the very informative talk. I have one question about the cluster counting PID, this huge improvement over the pure DEDX. Has this been verified in test beam, or is this from simulation only what you showed?
At the moment, is only from simulation. I have to say. There is an R&D program that is in progress, and we have plans to go to a test beam and demonstrate it fully. I know that in the past, some previous studies have been done, but okay. I agree with you. It has to be completely proven.
Yeah. Looking forward to seeing this. If I may a second remark, you said the hermeticity only starts at 100 milliradians due to the final focus. Now Tomohiko showed us that actually going even down to 5 milliradians is considered important for any sort of dark sector signatures searches. Has this been evaluated, what this means for the FCC dark sector physics program that you only start at 100 millirad?
No, not really. This is certainly something that will have to be evaluated. But I have to say, however, that the 100 millirads is for the big calorimeter and is ignoring the luminometer that of course can reach much lower. And however, the luminometer does not have full containment for hadronic particles. So you get some coverage from the luminometer down to very low. However, that coverage is incomplete. We will need to do really a full simulation to understand in detail how this will all play out. In any case, there is no way we can go farther down because it's really already very hard to make the quadrupole system so small. Making it even smaller is out of the question.
So how far does the LumiCal go down?
I don't remember the number.
Doesn't matter. I can sure look it up. Thanks a lot.
It's okay.
Okay, thank you very much for the talk and for the discussion. So now let's continue with another talk by Katharina Dort about silicon vertex and tracking detector R&D for CLIC.
Yes, thank you. I will share my screen. You should be able to see it.
Yes.
Okay, thank you very much. So let me start by saying thank you all for giving me the opportunity to present our work here. As introduced, I will talk about the silicon vertex and tracker R&D for CLIC. I will, okay, my slides don't, no. I will start with a brief introduction in the compact linear collider CLIC, then talk about some of our hybrid pixel detector assemblies, our fully monolithic ones, and then give a brief summary and outlook. Now, starting with the compact linear collider, it's a concept for post-LHC linear electron-positron collider. You see the footprint here. It would be built at CERN and comes in 3 different energy stages, and the highest energy stage would then go up to 3 TeV. The physics program includes some standard model top physics and Higgs physics, and also beyond the standard model physics, but there are some more talks which go into detail about this. This is the CLIC detector. And you see the inner 2 most detectors are the vertex and tracking detectors, which I will focus here in this talk. So these 2 detectors would be all silicon and they would be pixel detectors. Now coming to the requirements for the 2 detectors, I have here a list of all of the requirements. Of course, they arise mainly from physics. However, we pursue our R&D not specific to CLIC, but we profit, of course, from synergies with high luminosity LHC experiments, ILC, circular Higgs factories. So this means our R&D goes far beyond what is required for the CLIC experiment. Due to this reason, we also participate in a very strategic or a very wide strategic R&D program, the so-called EP-R&D, which was launched beginning of this year. And there's also a separate talk if you're interested. Now coming back to the requirements, so we look to meet timing resolution of about 5 nanoseconds, single point resolution of a few microns, of course, full efficiency of our sensors, low material budget, and low average power consumption. Of course, to meet all of these requirements simultaneously is a very challenging task. And for this, we have come up with a very broad, extensive R&D program, comprising both monolithic detectors and hybrid ones. And I will introduce some of them in the next couple of slides. And if I cannot cover all of them, so if you're interested, there's also more information in the backup or in our reports. Apart from the studies of the detectors themselves, we of course also develop instrumentation for beam test and data acquisition, but also for simulations and mechanics. And again, in the next couple of slides, there are some information, but detailed or more detailed information can be found in the backup or in our reports. Now I will start with the hybrid pixel detector assemblies, and I would like to introduce the CLIC-PIX2 readout ASIC. It's a 65 nanometer CMOS process, and it comes with a pixel pitch of 25 by 25 micrometer. So this is a very small pixel pitch, and we bump bonded this to planar silicon sensors of various thicknesses. And you see already this small pitch, and the bump bonding is of course a very challenging task. You see this down here, you have the sensor bump bonded to an ASIC and a small pixel pitch. As I said, the bump bonding is challenging. However, we have assemblies where we have an interconnect yield of above 99%. Also in beam tests, these assemblies performed very well, so position resolution of a few micrometer. However, this we achieved only for rather thick sensors, which do not comply with the material budget, of course. For thin sensors, this is more challenging. The timing resolution is down to 4 nanoseconds, and we are fully efficient. So in this regard, the detectors or the silicon detectors perform very well. The big challenge is, of course, this fine pitch bump bonding, as I said, is challenging. So we don't have a lot of well-connected assemblies, so the yield is rather low. And due to this reason, we also look at alternative interconnection technologies. So coming to the monolithic sensors, we look at two different processes, or two different technologies. This is the high voltage CMOS maps and the high resistivity CMOS maps. The high voltage CMOS is characterized by a large collection diode, which means you can apply a high bias voltage of a few hundred volts, meaning you can achieve a largely pleased volume and a high electric field inside the sensor, which then results in a fast charge collection via drift. In the next slide, I will specifically introduce the ATLAS-PIX Simple as an example. The high resistivity CMOS maps, on the other hand, are characterized by a small collection diode, which means the field inside the sensor is rather complex, it's inhomogeneous. However, you profit, of course, from the small collection diode in the sense that you get a low sensor capacitance, which then gives you a high signal to noise ratio and a low power consumption. And in the next slides, I will introduce a test chip called CLIC, where we have the small collection electrode design. Now, starting first with the ATLAS-PIX, the high voltage monolithic CMOS sensor. We have a pixel pitch where we have a strip-like pixel pitch, where we have one dimension where the pitch is large, one is rather small. And the ATLAS-PIX was designed in the Atlas ITK upgrade. However, this version with specifically the CLIC requirements in mind. And I will directly jump to the test beam results and focus specifically on our resistivity studies. So here we studied the efficient operation window for different resistivities. So here we have the efficiency on the y-axis, threshold on the x-axis. And you see for all of these assemblies, we achieve efficiencies of above 99%. However, if you have a high resistivity, you can increase this efficient operation window. And this is due to two reasons. So first of all, you get a larger depleted volume with a higher resistivity, which then gives you a higher signal to noise ratio. And second, the electric field inside the sensor is increased with a higher resistivity, meaning you get less charge sharing. So you have more charge collected by a single pixel cell, which increases the seed pixel signal and then gives you a higher efficiency. With the same argumentation, also the timing resolution is improved or improves with higher resistivity, this you see here. And the best result we have achieved so far is a timing of 6.8 nanoseconds. The only challenge for this chip is the spatial resolution. And for this, we also have a new submission with a modified pixel layout planned to improve the spatial resolution. It's a common development also with other experiments. And we expect first results in autumn or winter. Now coming to the small collection electrode CMOS design, as I said, we have the test chip called CLIC-TD. It's a 100 nanometer CMOS imaging process. And we have so-called channels, where we have again in one dimension we have a large pitch, in the other dimension we have a small one, and in this large pitch dimension we also segment the channel into so-called subpixels of a smaller pitch, and each of these subpixels has their own analog front end, and then 8 of these analog front ends are combined in one digital front end, meaning we can save space for the digital circuitry while still maintaining this the small pixel pitch and the small collection electrode design. Coming to the sensor process for the CLIC-TD, we have, so you see the process down here, and we have a P+ substrate on top of which an epitaxial layer of 30 micrometer is grown. In this epitaxial layer, we achieve full lateral depletion. So this is shown here, and then we have two different processes which we look at. So in one, we have a low-dose N-type implant inside the entire epitaxial layer, and in the other one, we segment this N-type implant, which gives you an additional, let's say, additional interface here, which means, and now to put it very visually, which means that you have.
We can hear you. Katharina, are you there? Does anybody else hear me?
We hear you, but we don't hear Katharina.
Yeah. So we lost her. She still has 1 or 2 minutes. Let's see if she reconnects. Well, she's not here. I guess we move on to another slide by Maryna Borysova.
Okay, let me share the screen. Okay. I hope you can see it full screen right now.
We do.
Okay, perfect. So I would like to present in this talk the recent research and development within FCAL collaboration on ultra-compact calorimetry, mainly designed for the forward region of E+ and minus colliders, but could be used in any experiments. In this talk, I will go through developed prototypes and dedicated electronics and their performance in different pin test campaigns, and also give some insight on future spin-offs. Forward calorimetry for future electron-positron linear colliders experiments have really challenging requirements on geometrical compactness, and three such calorimeters are considered to be installed into the forward E+ E minus in the forward region of E+ E minus collider experiments. So you can see layout for the forward region of ILD detector, and One of them, LumiCal detector, is needed to provide precise measurements of integrated luminosity. The design of it's a sampling calorimeter composed of 40 layers, in case of CLIC, 40 layers of fixed tungsten absorbers and a silicon sensor placed in 1 millimeter gap between absorber plates. Another detector, BeamCal, is designed for instant luminosity measurements and assisting beam tuning when included in fast feedback system. BeamCal has a similar design, and I mostly present here the results for LumiCal, but these results are applicable for any mentioned colorimeters. Luminosity measurement in E plus E minus classes can be measured by counting by events. In this case, the luminosity is obtained as a ratio of number of Baba events in some polar angle to the integral of differential cross-section. The differential cross-section could be precisely calculated but here I'm showing put the approximation in the leading order and also in the plot, and the range is defined by the fiducial volume of calorimeter, and for LumiCal baseline design, it was determined in simulation and shown with the vertical lines on this plot. The optimization was done in simulation, and on the plot to the right, you can see the image resolution of LumiCal as function of polar angle, and we can and here we can determine the fiducial volume of calorimeter, and here it's also indicated with vertical lines. The statistical uncertainty for luminosity measurement is defined by events registered by LumiCal, and it means that keeping the fiducial volume in polar angle as large as possible allows reducing the statistical uncertainty of luminosity measurement. It is achieved by designing a calorimeter with a small Maillet radius. Also, small Maillet radius, very important for BeamCal. The design of LumiCal sensor was optimized in simulation to provide the required resolution of polar angle reconstruction. And LumiCal silicon sensor could be seen here. It's shaped as a ring segment of 30 degrees and subdivided in 4 sectors, 7.5 degrees each. There are 64 radial pads in each sector and with a pitch of 1.8 millimeters. So the sensor is about 11 centimeters long and inner radius is 80 millimeters. And it's made of N-type silicon with a thickness of 320 microns. The LumiCal, the compactness of calorimeter is achieved by thin module design, and as shown here in current LumiCal, the space between absorbers is 1 millimeter, and the developed procedure for model assembly provides the detector model of about 650 micron. In this assembly, 2 thin captain parts used to supply high voltage and to connect the readout electronics to the sensor. The first one connected with the conductive glue, and captain cup of an out is connected with wire bonding. Special carbon fiber support provides mechanical stiffness and facilitates the handling and mounting on tungsten plates. The dedicated readout ASIC was developed. It has a name Flame, and this is complete readout ASIC with the full functionality, including front-end readout ADC and biasing and calibration. It's 32 mixed mode channel. Each channel comprises variable gain front end 10-bit ADC with sampling rate up to 50 megasamples per second and ultra low power consumption. Also, it's really important to get a highly compact structure structure, highly flat tungsten plates are needed. And this were produced from a special alloy, and the measurements showed that the flatness of these tungsten plates were achieved better than 30 microns. These tungsten plates were glued to permaglass frame that accurately determines their position in a calorimeter stack. Throughout the years, we had several performance tests of LumiCal prototype. The first test in 2014 was aimed to test multi-plane detector operation. So we had 4 LumiCal detector planes, silicon plates placed in 4.5 millimeter gaps between tungsten plates, and they were tested with 5 GeV electron and muon beams. The next campaign was aimed to study compact design, and in these studies we had 8 LumiCal detector planes equipped with adapted APV25 readout, and they were placed in 1 millimeter gaps between tungsten plates and tested at DESI. The most recent campaign was done in March 2020, and the deep compact design was tested with 15 layers of calorimeter, and more important, with dedicated electronics-free planes were equipped with it. The main goal of campaign in 2016 was to study compact design, and to study also the electron gamma separation. The geometry and stuff for this study could be seen here, and it was optimized in simulation just to be able to distinguish in calorimeter to separate showers from that were coming from the electrons and from the photons. Some highlights, the results from these measurements are given on this slide on a plot top to the left. You can see the longitudinal shower development. The maximum is reached in layer 7, and both distribution within statistical uncertainties in reasonable agreement. Bottom left plot shows position, radial position residuals between the calorimeter and tracking planes, and the resolution that could be estimated to be 440 microns for 5 GeV electrons, and it is in agreement with this simulation and design for HL-LHC images. Also, segmentation, our sensor is rather specific, and we developed the methods in 2014 to account for circular shape to measure Mollier radius. We use the parameterization of transverse profile, which has 2 items. One is describing the core, another the tails. And the plot in the middle shows that the transverse shower profile both for data in Monte Carlo, and from this effective Mollier radius is found to be at 8 millimeters. Also, these facilities allows to measure different electron beams, and which were used to study the calorimeter response. The figure to the left shows the distribution of energy deposited in the calorimeter for electrons of different energies. Also, in a plot in the middle, you can see the effective Mollier radius as a function of electron energy, and observed slight dependence on energy is explained by the fact that we had a limited number of planes in prototype, and full simulation shows that of fully instrumented calorimeter doesn't show any energy dependence. Also, in these measurements, we had photon electron identification efficiency estimated, and it is better than 90%. In the most recent campaign, which was rather difficult because it was just performed before lockdown, and due to COVID-19 in China, it was hard to get ready for the beam test. In this beam test campaign, we also measured energy edge scan for fiducial volume studies, and also collected the data with total calorimeter to study the reconstruction of tracks in ILC-like geometry. And this first test was rather successful, and data analysis just is in progress. And this brings me to my summary. HL developed a design for the very forward region for the experimental E+ E- colliders. 3 compact calorimeters are foreseen: LumiCal for the precise measurement of integrated luminosity, BeamCal for bunch by bunch luminosity measurement and electron tagging, LHeC to extend the coverage of HL. The sensors for prototype of LumiCal are designed and fabricated. Dedicated ASICs were designed and also fabricated. Prototypes of fully instrumented detector planes are built and tested. Prototype of highly compact calorimeter was studied in different beam test campaigns. The measured effective molecular radius is 8 millimeters, and the measurement of shower position reconstruction is 440 microns resolution for 5 GeV electrons. All the simulations were confirmed by the measurements, and these technologies that were developed by HL are applied in other experiments, for example, in CMS and XFAIL, and now are considered for LHeC experiment at DESI. That's it. Thank you very much.
No, thank you very much. Are there any questions for Maryna?
Hello, can you hear me? Perhaps a naive question. Yeah. I think you focused very much on the measuring the electrons, but you should have as well converted photons. And then you could also measure the photon. Yeah,
we did this measurement. I don't show any plots today, but the studies are just ongoing. But yes, we did the studies, as you can see. Here on the slide, on this slide, that we use target to convert electrons to the photons and measure them simultaneously in the calorimeter.
Excellent, because then you have even better control of stability of luminosities.
Sure, yeah. Hopefully we will have more results and plots to show.
Okay, if there are no more questions, so thank you, Maryna. So I see that Katharina is back, and I think she can finish her presentation.
Yeah, thank you very much. I'm sorry again for the technical interruption. I think it was somewhere this slide or the next one that was interrupted.
Yeah, I think you can continue.
Okay, I will continue with this slide. I don't know exactly where my connection broke off, but maybe just to continue here. So as I said, with these with 2 sensor processes, if you have the gap in the N layer, you get an accelerated charge collection and therefore improved timing resolution and reduced charge sharing. Reduced charge sharing you see especially here if you look at the efficiency against threshold. For the gap in the N layer, you get a higher efficient operation window, which is of course extremely relevant if you go to very thin sensors where you only get a small signal in the sensor. Now, on the next slide, I would like to focus a bit more on how this sensor processes were optimized. This was done in 3D TCAD simulation and then verified by a combination of sensor simulation coming from 3D TCAD with a Monte Carlo framework, which then gives you high statistics. And you see this result here. So here you have an in-pixel map of the timing resolution. And you see very well that you need, of course, high statistics to even make these kind of plots. And what you also see here is that the timing resolution is especially bad in the pixel corners for the continuous N layer. However, if you introduce this gap, you can improve there significantly. And especially in our case, where we introduced gap only in one spatial dimension, you also see that this improvement is more pronounced in the spatial dimension where the gap is introduced. Now, to drive this even further, we optimized even further by going to a hexagonal pixel design. This was done in the so-called attracted fast-pix chip. And with the hexagonal pixel, you have two additional improvements. First of all, you reduce the minimum distance to collection diode. And second, you go to a hexagonal grid, meaning you reduce the number of nearest neighbors. And all of these optimization studies are, of course, essential for future sensor designs, especially in 65 nanometer technology. Now, to summarize and give a brief outlook, you have seen we have a very broad silicon detector R&D with both hybrid and monolithic designs, and we have achieved so far several important milestones which go far beyond the requirements for the CLIC experiment. Meaning we consider our R&D very generic to develop tomorrow's silicon detectors. And due to this, as I introduced in the beginning, we participate in this strategic R&D program, the EP R&D, which does not only develop new silicon detectors, but also covers other instrumentations. As an outlook, we look forward to exploring more different or alternative interconnection techniques, and also to develop or to have future development in monolithic sensor designs, especially, of course, for 65 nanometers. Thank you.
Thank you very much. Now, are there any questions to Katharina? I don't see any raised hands, so just a quick question from me. So the ILC is planning to use the chips with the power pulsing. Do you also consider this power pulsing for the pixel chips for CLIC?
Exactly. So for the power pulsing, this we have here in the backup. So the beam structure of CLIC also comes in these kind of bunch trains. So we have a very low duty cycles between these bunch trains, and with the same argumentation, we can also then go to power pulsing. And we also had some studies already with the power pulsing. So this is now for the CLIC-PIX2 chip, or ASIC, which are introduced in the beginning. And we have seen that we can so far reduce the power by a factor of 5 with the CLIC-PIX2. But we know that we can have additional improvements where we can reduce it even more by a factor of 80. So we do consider the power pulsing, and we also study it already.
Okay, the factor of 80 would be, I think, quite impressive. Okay, thank you very much. And now let's continue with Jana Faltova and design and performance studies of the calorimeter system for an FCC-hh experiment. We can hear you. We don't hear you, Jana.
Sorry, and now we can hear me, I guess.
Yeah.
Sorry. So I will share the slides. Okay, so now you can hear me and you can see the slides, all right?
Yes.
Perfect. So the topic of my talk is the calorimeters for the FCC-hh experiment. I don't really have to introduce the FCC project, as you have already heard about the FCC-hh and the IDEA detector. So just briefly about the hadron collider, which is also the part of the future Kilo Collider project. And it defines the length of the tunnel, for example. So we consider a 100 kilometer long tunnel with 16 Tesla magnets, which will give you the center of mass energy for the proton-proton collisions of 100 TeV. And it is one of the goals of the FCC project. We delivered the conceptual design report for the European strategy update, which was quite then optimistic for us, I would say. And you can find the reports on the link on my page. Going to the next slide, I would like to briefly summarize the parameters of the FCC-hh machine. Here you have the comparison with the high luminosity LHC, and this column is for the FCC-hh. So we have almost an order of magnitude larger energy of the collisions. Also the energy, the magnetic field is much larger. But what is like the important part for us from the detector part is the especially the pileup, which we have in the running scenario 2. We expect the pileup with the average number of collisions of about 1,000, which is 5 times more what is expected for the high luminosity LHC. And in total, over 25 years of the operation of the machine, we would like to collect of about 20 inverse afterburn of data. The reference detector, which was designed or think of for the FCC-hh, is not the only possibility, but it is one of the options which we studied to show the feasibility of the project, that we can really deal with the very, very high radiation and also the high pileup. Another thing which we wanted to really have was the very hermetic coverage, where we wanted to be able to measure jets up to eta 6. So the design was very much inspired by the experience from the LHC experiments. So at the first look, if you have a look in the detector, like the center part looks very similar to what is in CMS, that we have the calorimeters inside the 4 Tesla magnetic field, and then there are muon chambers outside. And then we added kind of like LHCb style detectors in front to be able to really cover the pseudo-rapidity range. We have developed a software package to be able to run the simulations, the fast and full simulations. I will concentrate on the calorimeter system, which is basically very much the Atlas style. We have the liquid argon technology for the center barrels, the electromagnetic calorimeter, and also in the forward region for the hadronic calorimeter as well. And then the hadronic calorimeter, the barrel, is designed with the scintillating tiles and steel and lead absorbers. I have to show really the radiation doses which I'm like talking about. So here I have a plot for 1 MeV neutron equivalent fluence for 30 inverse afterburn. And like the most hot spots are the central tracker and also the forward calorimeters, where we have the fluence up to of the order of 10 to 8 per centimeter square. Basically, like the numbers we have are 10 to 30 times worse than for what is foreseen for high luminosity LHC. So let me go really to the calorimeters. Let me start with the electromagnetic calorimeter, where we took the liquid argon, or we considered the liquid argon calorimeter. There are several reasons for that. One of them is that it is really very radiation hard. We can even use this material in the forward region. And we have also very good experience with such a type of calorimeter from Atlas, that the response is very linear, uniform, and the calorimeter is very stable. But we did not just like make a copy of the Atlas calorimeter, but there are several advantages of our new design. We don't take the accordion structure, but we have a design with a straight multi-layers electrodes, which are placed in the middle of the inclined lead plates. With this, we can have a really fine segmentation, both in lateral and also longitudinal direction. You can see like the details here in this place. So let me show a bit more about some of the performance results which we have from the Gianfranca simulations. Our goal was to have a sampling term better than 10% or 10% or better, and the constant term below 1%, which we achieved. You can see here, like this is the energy resolution for electrons with different pileup scenarios. So of course, with increasing in time pileup, the performance degrades, and we end up with a really like large noise storm of 1.3 GeV. So this is something which we have to work on, that we really need to add some ways to reduce the pileup effects. If you propagate these results to the diphoton decay of the Higgs boson, or you also simulate this, so we still have really nice resolution, even if we consider such a high pileup. And this is one of the goal of the FCC-hh, that we claim that we can really measure the Higgs self-coupling with a very nice precision. And this we think that we really can with our eCal concept. Another thing which I want to mention is that the concept is also interesting for the FCC-hh collider. But for this, we need to do like a different kind of optimization to be able to measure to very low energies also. So let me go to the center hadronic calorimeter, which is done with a scintillating tiles perpendicular to the beam axis and the steel and lead absorbers, stainless steel and lead absorbers. We also manage like to have a design with much higher granularity compared to Atlas, with 10 longitudinal layers and the size of the cells as you can see in the slides. The way how the segmentation is done, it is not like the smallest we can go even further, but this is also something to be studied, what is like the optimal size of the cells. It is read out with the silicon PMs, and we would like to use also to be able to run such a calorimeter. We need calibration systems, which we have also the very good experience from Atlas. First tests with the tiles of the FCC-hh size, the wavelength shifting fibers and the silicon PMs were done in the laboratory, and the results are promising. This is the combined performance of the calorimeter systems for the simulations, Gianfranca simulations of single pions. For this, we used really only the calorimeters. No reconstruction in the calorimeter was done for that. And if we use the conventional calibration, we end up with a constant term, or so the sampling term of the order of 50% and the 2% constant term. But this does not really profit that much of the fine granularity that we have. So if we try to have the performance also, or the reconstruction with more advanced techniques, we tried the deep neural network. where we also, the input was only the fine granularity cells from calorimeters. So we end up with a sampling term of 37% over square root of E, which is really promising. And this is something which we have to work on to really like have a particle flow algorithm running for our calorimeters.
1 minute remaining.
Yes, I'm almost at the end. Thank you. So this was basically just based on the simulations, but there are also EP R&D projects related to our calorimeters, especially the liquid argon calorimeter, where we would like to test and design really the readout electrodes. Then another thing which is important for us, the high density feed-throughs, as we will have much more cables compared to what is in Atlas, and also what is crucial for the energy resolution is the material in the cryostat. So we are there is also a project on the ultra thin cryostat for future experiments, and I cannot forget about the software development project, which is also it is not only for calorimeters, but it is the calorimeters are also included in that. So here in the summary slide, I just would like to say that we designed, optimized, and documented our calorimeter system. We found out that we managed to fulfill the physics requirements based on the simulations, and now we are starting with the R&D projects to develop the necessary hardware. And you can, if you are interested in more details, please go into these two references. For example, like the second one, it is really like 100-page document, so we can find quite some details. Thank you for your attention.
Thank you very much, Jana. Now, are there any questions? We have time for one short question.
Yes. You mentioned the possibility to use the liquid argon ECAL also in the forward region. Is it compatible with the expected rate in this region?
Sorry, I did not get the second part.
Is the liquid argon solution for the ECAL
Yes.
compatible with the expected rates in the forward region?
Yeah, worried about.
Sorry.
Well, the resolution or about what?
I'm thinking about the timing.
The timing. All right. So the timing of the detector is something which we have to look at, but like basically like the liquid argon calorimeters have a very good timing resolution. For example, in Atlas, it's of the order of, okay, but I don't want to, I think it was about around 30 picoseconds, but I don't want to give you bad numbers. I don't like remember, and I haven't checked. But this is something like to be studied, the timing resolution. But we don't have like bad timing resolution. Like
actually, I was more thinking of the shaping time.
Yeah, so this is something to be studied. We really haven't checked, I have to say.
Okay, if there are no more questions, let's continue to the next presentation, which is by Vincent Boudry about the implementation of large imaging calorimeters.
So I'll try to share my screen. Okay, do you see my screen now?
Yeah, we see your slides and hear you loud and clear.
Okay, thank you. So it's my pleasure actually to present the work from the CLIC collaboration on the recent technological prototypes that have been built in order to test the feasibility of large imaging calorimeters. So that will be one of the first of two talks on the CLIC prototype. Here I will focus more on the technical aspects, and Wataru in the next presentation will show you the physical measurements made with actually the previous version of those prototypes. So I was mentioned earlier for particle flow optimized detectors. we rely on high precision tracking, but also on calorimeters that are able to disentangle the contribution from the individual particles. And that's why we call them imaging devices, because we have images of the showers in the calorimeters. And this requires very high granular calorimeters, typically using hundreds of millions of cells for the HL, with cell size typically of the order of the centimeters or below, and between 25 and 50 layers in each of the calorimeters. And the CLIC collaboration has been built actually to design and operate such prototypes and check all the possible conditions to make this work. So I will present actually 4 prototypes, 2 ECALs and 2 HCALs. The ECALs will use tungsten as absorber material because we have much compactor showers with that, and the HCAL iron. 3 of them have an analog readout, so that's the silicon ECAL, scintillator ECAL, and scintillator HCAL. And 1 uses a semi-digital readout of gaseous sensors. Okay. So all those prototypes are actually built around a common set of very front-end chips, which were produced by the Omega Group in Palaiseau. All those chips take advantage of the power pulsing allowed by the HL-LHC to limit the power consumption, which is a key issue here. They emphasize low noise preamplifications, high precision ADC, and type of nanosecond TDC implemented directly into the chip. So inside, we have this precision inside of the calorimeters. And importantly, we have self-trigger on individual cells, and that allows for delayed readout, so local storage of the data and delayed readout between the bunch trains. And the design has been made so that we can have high integrations of the electronics inside the detectors. So this integration actually takes place in such cassettes, which are folded into structures, into the ECAL and HCALs. Such cassettes typically allow for tens of thousands of cells or between 200 and 500 ASICs, which have to be power pulsed and still be sensitive to the MIP signal, because we want to track particles in the calorimeters. The prototypes that have the prototypes which are built now are really a very small subset, a fraction of a % of what is needed at the end. Nevertheless, they are a good test stands also to test the reproducibility of the design and scalability. Concerning the DIQ, there are actually low requirements except on the placement. We have only something like 3 to 5 centimeters between the calorimeters or the calorimeters and the coil, and the readout has to take place in this region. So that's a minor issue, but we have to do this readout only on one side of those cassettes to minimize the dead space. What is more challenging is the power pulsing, bringing the power here in a 3 to 4 Tesla field. And to cool everything, we aim to have only passive cooling on one side of the calorimeters. So we have to extract all the heat also on this side. Concerning the very front-end electronics, there are still some R&D which is needed. The current version of the chips are not good enough for the final implementation, especially for the HL-LHC. And such a cycle of development takes typically more than 3 years. So we are almost already short in time for the HL-LHC timeline. One of the questions is whether or not we should improve on the timing measurements. We are learning from the CMS HL ASICs, and we know that we have realized that this is a hot topic, and we have much to gain from that. some common features between all the prototypes is also the measurements which have to be done. So there are some scientific goals. Of course, you want to measure, ensure the proper measurement of the energy, time, etc. This has been done mainly with the previous generation of detectors, so-called physics prototype, and that will be presented in next presentation by Wataru. What I will focus here is really the technical goals using those scalable designs, make them work with power pulsing operation, and check that the low energy response is proper, because we have to mitigate the noise, given that we have limited memory in the chips, and that's a very important measurement to be done, that we are able to trigger here without filling the memories. Check that we have proper uniformity of the response. And also we have to feed the simulation models so that we can properly model the prototypes and the particle flow processes in the real detectors. And for this, we have to make real digitization models. So this is one of very important aspects of those tests now. Once all this is fulfilled, we can do also again all the scientific goals that has been done during the last 10 years. Okay, on the prototype, I will start with the, let's say, historical one, which is the silicon tungsten nickel. There we go to extreme granularity with half a centimeter size for the cells, and we take advantage of silicon, which is both versatile in sharing and as an intrinsic stability. And wafers, pin diodes, high resistive pin diodes are glued directly onto the PCB. And a big effort has been done on the design of this PCB, which is very challenging. You see here from the name of the board that we are already on the version 13 of them, with some attempt also to put the readout either on embedded packaged chips or embedding them directly inside the PCB in order to gain on the thickness. We are now at the stage where we can, we have 15 layers made of the various versions we have built so far, also with different thicknesses of the wafers. They are all integrated in a new structure with a new DIQ, which allows them to read them very reliably, which was not always the case before. And this DIQ is also a kind of a prototype for the ILD, so that because it fits the dimensions needed for the final detectors. Here, the game is actually to mitigate the noise, and that was quite some work. And now we are able to have, you see here, a map where the white cells are the masked channels. That has been a long work, starting in 2015. And if you check at the signal to noise ratio, here it went from 16 to more than 30 by improving both the PCB and also to go by going to thicker wafers, which allows which brings an immediate gain on the signal strength. But this signal to noise ratio, this is in the readout branch. What matters is the trigger branch, where it's less than in the ADC branch. But there again, we are over the requirements of a factor of 10, and we're able to trigger at a third of a MIP while keeping 4 sigma cut on the noise. So we are now ready to go for large test beam and test with particles. And you see here that we still are also, we have to take care of those missing cells in order to correct the effect. Having very narrow showers actually makes you also very sensitive to single missing cells. So we should have been in test beam in March, that was cancelled. So we'll go again in November. There were also some tests to go into to test long slab, and we have seen some defects here. That has been corrected, and we are wondering about switching to 8 inches wafer because it brings many advantages in terms of design and performances. That's still some R&Ds ongoing. The question of the cost actually could be of the ECAL. One of the solutions would be to go to use scintillators, and that's one of the solutions that has been designed. So here the readout is made by using strips of scintillators of 5 millimeters by 45 millimeters, or double this size. And you can hope to mimic the same granularity as for the silicon by actually having the strips orthogonally placed here in a single layers. Now, this solution has been developed in physical prototype for 4 years, but it was renewed with the technological prototypes recently by a collaboration between a Japanese group working on the HL-LHC and Chinese group working on the CEPC. And they have now a prototype which is almost ready with 32 layers built. They used 2 types of SIPM, also from Hamamatsu, which are directly glued on the PCB. Yes. One of the challenge here is actually the coupling between the strips and the scintillators, and there have been quite some R&Ds here to fulfill that properly. They benefited a lot from the experience from the HL prototype that has been developed for many years. This prototype features 3 by 3 tiles molded, individually wrapped. And they have now 38 layers, which have been put into a test stand, either alone or as the 3rd section from the CMS-HH. And now they are ready to go with combined beams with the ECAL as soon as we're ready. Here the challenge is actually that you should perform uniformity of the response and correction of the gains, since SIPM are not always stable versus the temperature and high voltage. Statistical saturation should be also corrected, and this is seems to be achieved until 350 MIPS in individual cells. Recent developments features the measurement of the effective timing resolution, which is close to the goal, and various techniques actually allows you also, due to the high granularity, to measure directly some intrinsic parameters of the prototype, such as the lambda, make some online particle identifications quite easily, and also clean up the neutron delayed response in the showers using the timing. There are some R&Ds going on also to make the prototypes more industrial easily by building mega tiles in which the tiles are not separated, and this is ongoing development. And after some search, the next test beam should hopefully show better results here on the uniformity of the response. There are also some R&D on the needed precision for the positioning of the tiles. You see here a misplacement by less than 1 millimeter brings some non-uniformities. Long layers as for the ECAL. And next month also will take place the first test of the PCB for the CMS-HH. So that's a lot of developments which are very active. Very last prototype, this is that is an alternative to the HCAL. This is the semi-digital gaseous HCAL, on which thin gaseous resistive plate chambers are read out with a granularity which is 9 times the one of the HCAL, but which is read with semi-digital calorimetry, which is counting only using 3 threshold. And you see here showers with the 3 threshold, and you see that the highest threshold in red occurs mostly in the core of the showers. Nevertheless, with such simplistic counting, it is this device is able to achieve energy resolution which is comparable with the HCAL. The difficulty is the threshold optimization, because the optimization, the calibration has to be done by scans. and to make a reliable digitization, which is very complex due to the many overlapping effects in the detectors. And this is something that has improved quite recently, and now we think it's reasonable until 40 GeV, which is an important input for the simulations.
We should finish.
I go to the conclusion. So here also some development with large RPCs. We should go to 3 meters, and we have no devices with 1 meters. Large PCBs, which should be flat enough, and work on the structure, which has to be done using electron beam welding to ensure stiffness and precision. Okay, so conclusion. So we have a lot of new prototypes that are available now or has been for the last years. This is well in timeline with HL-LHC, given the time of R&D. We have many information which has only been partly explored. So there is a lot of work for additional analysis and new ideas using this information, as well as many small-scale R&Ds which are needed to ensure that we have all the needed precision on all the elements. I will finish with a very last word on CALIS. So it's been 15 years of R&D where we had many collaboration between even competitive designs. And it has opened recently beyond the HL-LHC to other kind of activities. So you are very welcome also to bring or show your ideas for discussion during the collaboration meetings. Thank you, and sorry for the
no problem. Thank you. Are there any questions for Vincent? Yes, Sasha?
Yeah, thank you. I would like to ask about tungsten silicon calorimeter. So you showed that the silicon sensors becomes thicker, starting from 320 to 5600. Is there a reason for that? And for 8-inch, you are going to 700 even. Is that correct, microns?
Yes. So the idea is there that we would like, for cost reasons, to reduce the number of layers we use. And you can recover a part of the resolution by using thicker wafers because you improved the amount of the signal. And this reduces also the noise. So we see many advantages in going to this 700 micron wafers.
Okay, thank you.
So thank you, Vincent. One more time, I have a quick announcement to make. I was asked by the conference organizers that we make a group picture, and I think we should do it just before the coffee break. And especially I was asked if the participants can produce the funny faces. That would be very nice for the PR of this conference. So let's prepare for that, and now continue with Wataru and the structure of hadronic showers in highly granular calorimeters.
Okay, I hope you can hear me. And let me share my.
But Vincent
slide.
is still sharing.
Yeah.
If you can unshare,
yes,
then
sorry.
Wataru can.
Okay, thank you. Okay, I hope you can see my presentation.
Yeah, can you try full screen?
Yeah.
Perfect.
Okay, so let me start. Okay, first of all, I appreciate this opportunity to present our work in this conference. Okay, in the previous talk, the Vincent presented technical implementation of a CALIS high granularity calorimeters. And here I would like to present some results from the test beam experiment with the CALIS highly granular calorimeter prototypes. Okay, the physics at the future electron positron collider experiments requires jet energy resolutions as good as 3 to 4%. And our idea is to achieve this unprecedented jet energy resolution by the particle calorimetry, where we measure the energy of each particle in a jet with best suited detectors. And but this PFA concept requires the high granularity calorimeters. And the CLIC collaboration has been developing this high granularity calorimeters. And as shown in these pictures, different groups are working on the several technology options for this high granularity calorimeters. Okay, and the collaboration has developed the several test beam prototypes as shown in these pictures. And actually, we started with the physics prototypes. It's full layer test beam prototypes for proof of principle of high granularity calorimeter concept. And now we are moving to the technological prototypes. This is to demonstrate the good performance with a more realistic implementation, as presented by the Vincent in the previous talk. And for instance, here we have a silicon-based, silicon sensor-based tungsten incl, and here we have a scintillator strips-based tungsten incl. And for the HL, we have a scintillator tiles-based analog readout HL called HL. And we also have a HL with the glass RPC with the digital or semi-digital readout, so-called DHL or SDHL. So I will show some results from the test beam experiments with these test beam prototypes. Okay, so we put the emphasis on the study on the hadronic shower, because hadronic showers are quite complex, and as shown in this picture, typically there's a narrow core of electromagnetic cascade, which is surrounded by the halo dominated by the charged hadrons. The biggest problem is that we suffer from the large event-by-event fluctuation of electromagnetic to hadronic components ratio. So this makes it quite difficult to properly reconstruct the hadronic energy of the hadronic shower. So the correct understanding of the hadronic shower is quite crucial. In addition, the simulation of the hadronic shower is not trivial at all. And actually, the modeling of the hadronic shower of the Giant4 is not perfect. And actually, the CLIC test beam data provides useful information to validate the Giant4 shower model. So here I will present some results from the test beam experiments with the emphasis on the study on the hadronic shower. So let me start with the results by the HL, scintillator-based analog HL. And this shows the measured longitudinal heat energy distributions for the pion and also the proton, 30 GeV. And this measured profile analyzed by the function with the two components, the short and the long components, which basically corresponds to the electromagnetic and hadronic components. And in this way, we can decompose the two components as shown in this picture, and we can extract the ratio of hadronic to electromagnetic response, H/E, as shown in this picture, which is as a function of a beam energy. And this shows the reasonably good agreement with the simulation. And it's also consistent with the previous measurement by the CDF and Atlas calorimeters. And the semi-digital HL, SDHL, which has the finer transverse segmentation, is useful for the study on the radial profile. And actually, this is the measured radial heat distribution by the measured by the SDHL for the 20 GeV and 70 GeV pion. And you can see that the bit wider radial profile in data compared to the simulation. And this discrepancy is under investigation. Okay, hadronic shower can also be studied even by the ECAL, CLIC ECAL, but with the low energy hadrons. And actually, this is the measured longitudinal energy distribution for 10 GeV pion. And you can see that the some discrepancy compared to the simulation. And okay, here it shows the mean of longitudinal heat distribution. Here we see the good agreement between the Monte Carlo and the data. And on the other hand, we see some disagreement in individual heat energy. And it may be explain the this discrepancy in the longitudinal energy distribution. Okay, another interesting tool with our calorimeters is track segments. Thanks to the high granularity of the calorimeters, we can identify the track segments within hadronic showers. And this is the example of the event display taken by the HL-LHC for the 50 GB pion. And this LHeC is identified the track segments. And this track segments within shower can be used for the, of course, the detailed shower study. And it can be also used for the in situ calibration of the detectors. And actually, it can also improve the energy reconstructions. Actually, for the HL-LHC, by giving the optimized weight for the hits on the this identified track segments, we can improve the energy resolutions, especially for the higher energies. On the similar studies were done also by the silicon tungsten incl and also HL. And actually, this is the measured energy, measured distribution of the energy deposit on the track segments by the silicon tungsten incl. And they look like distribution. So this indicates that this can be used for the in situ detector calibration. And this shows the mean track multiplicity measured by the HL, and it shows good agreement with the simulation. Okay, and another important topic is the reconstruction of the energy of the hadronic shower. And as I said at the beginning, the energy reconstruction of the hadronic shower is quite difficult because of large fluctuation, event-by-event fluctuation of the E/H ratio. And the idea is here is to compensate this E/H by assigning the different weight depending on the energy densities, because we expect the higher shower density for the electromagnetic component, while lower density for the hadronic component. So this so-called software compensation technique was tested by the combination of the carrier scintillator-based calorimeters. And actually, we observed the significant improvement of the energy resolutions by 10 to 20%, as shown in these pictures. Okay, the similar thing can be done for the SD semi-digital HL. And the energy reconstruction of the SD HL is based on the multi-thresholds readout, and as shown in this equation. And this N1, N2, and N3 are the exclusive number of hits associated to the 3 different thresholds. And by giving the optimized weight, alpha, beta, gamma for these numbers, we can have a optimal reconstruction of the energy. And actually, okay, thank you. And this, the so-called multi-threshold modes, we observed the improvement of the energy resolution compared to the binary mode, where we can just sum up the number of hits. Okay, so this is kind of SD-HL version of a software compensation, and it works. Okay, the timing structure of the hadronic timing is also another important tool for to enhance the performance of the calorimeters. And actually, we measured the time structure of the hadronic shower at the CARIS T3B experiment, and where we placed the small dedicated setup composed of 15 centimeter tiles just behind the CARIS hadron calorimeters with the tungsten and or steel absorbers. And as shown in these pictures, for instance, we observe more rate component in tungsten absorbers than in steel absorbers. This is kind of as expected. And for the recent technological prototype, we now have a capability of heat time measurement by the calorimeter itself. And actually, this is the measured timing heat time resolutions for muons by the HL technological prototypes. And it's 1.6 nanosecond. And which is not striking, but please note that this is currently limited by the issues of the front-end electronics. So we are improving it. Okay, so this brings me to the summary, and high granularity calorimeters for future electron-positron collider is under development by the CARIS collaboration. And high granularity is a key to the unprecedented jet energy resolutions for the particle flow calorimetry. And as I showed, we can study in detail the hadronic showers with the test beam prototypes with high granularity. And actually, the most of the result I showed today come from the test beam experiment with the physics prototypes. And as I said, at the beginning, we are now moving to the technological prototypes, and so we expect to have a more, let's say, the better results soon to arrive from this test beam experiment with this technological prototypes. So please stay tuned on the CARIS collaboration. Okay, that's it. Thank you.
Thank you, Wataru, for a nice talk. So does anybody have question? If yes, please raise your hand. I don't see any raised hands, so I will just have a quick question, maybe a naive one. Do you have an idea, or can you comment about the source of the small discrepancies between the measured data and the Gianfranca simulation? And do you plan to tune the Gianfranca models for your purposes?
Okay, it's a difficult question. Also, it depends on the. Okay, we have several prototypes, and we saw some discrepancy with the prediction by the Gianfranca simulation, and probably the reason are not let's say are not single. I mean, we have different reasons for that, and actually we are working on it, and together with the Gianfranca collaboration.
Okay, thank you very much, Wataru. So now let's continue with Emmanuel Francois Perez and physics opportunities and detector challenges for a Tera-Z factory.
Hello, everybody. Can you hear me well?
Yes.
All right, so let me share.
Yes, very good.
Okay. Oops. All right, so I will present some physics opportunities at a Tera-Z collider and some subsequent requirements on the detectors with a focus on the FCC project. So in the FCC CDR released last year, two detector concepts are described. One that is derived from the CLIC detector and the other one that was presented this morning by Franco. So they both comply with the tight constraints imposed by the machine detector interface and with requirements imposed by basic physics analysis. In this example of the Higgs events, you want the reconstruction of the recoil mass to be limited by the beam energy spread and not by the detector resolution. However, at Tera-Z, the statistical uncertainties on all measurements will be very small, which in turn calls for very small systematic uncertainties. And designing a detector that will allow the systematic uncertainties to be commensurate with the statistical ones comes with challenges that were not studied in the past and that we are trying to identify. So this is the FCC-hh operational mode as considered, with 4 years at the Z-pole and then at higher energies. So at the Z-pole, 150 inverse attobarns would be collected by 2 experiments. So compared to LHeC, the statistical errors on the Z-pole measurements will be reduced by a factor of 500. So this luminosity corresponds to 5 10 to the 12 produced Z's, hence the Tera-Z name, and to these numbers of B and tau pairs. So it is also a B, a charm, and a tau factory. So these huge statistics will allow very high precision electric measurements, which via the loops offer sensitivity to new physics with a scale as high as 70 TeV. And new physics may also be discovered in very rare standard model processes, like those involving Lepton favor violation, or via the direct production of very weakly coupled particles, right-handed neutrinos, for example. So this table here lists the electroweak precision observables that FCC will measure at the Z-pole. The current uncertainty is shown in the second column, followed by the statistical uncertainty at FCC-hh, and by first guesstimates of the systematics. In most cases, we are working on reducing them. One source of systematics that has been studied in detail, though, is the knowledge of the center of mass energy. So at FCC, at the Z-pole, Root S will be known to 100 keV, so 20 times better than at LHeC, thanks to resonant depolarization measurements. And this is the key for the exquisite precision for several observables, in particular the Z mass, which will be determined to better than 100 keV, the uncertainty on the width being 25 keV, for the effective mixing angle, which will be measured to a few tens to -6, and for alpha QED, which will be uniquely determined directly at MZ. And while the detector requirements for these measurements are not expected to be challenging, others that are highlighted in orange in the table set more stringent requirements. So that is the case in particular for the number of light neutrino species. The measurement from LHeC still sets today one of the most stringent constraints on the BSM neutrino mass models. So this is determined from the total cross-section, hence the luminosity measurement is a key. So the luminosity will be measured from the rate of small angle Baba events, measured in 2 forward calorimeters, similar to those proposed for ILC, but at only 1 meter from the interaction point. And you can see it here, immersed in the CLD detector. These are these little red squares here. And this is the radial dimensions. And the goal will be to reach an experimental uncertainty of 10 to the -4 on the absolute normalization, which would then match the anticipated uncertainty of theoretical origin and lead to a reduction of the uncertainty of the number of light neutrinos by a factor of 8. So the key is then to know your acceptance within 10 to the -4. So as done at LHeC, we would define a narrow and a wide acceptance, and an asymmetric selection will be made. So for example, you demand that the electron on one side is in the narrow acceptance and the positron on the other side is in the wide acceptance, or the other way. So the advantage of such an asymmetric selection is that the dependence of the acceptance on any radial or longitudinal displacement of the interaction point with respect to the luminometer system is cancelled to first order. And by defining the wide acceptance as being larger than the narrow by 2 millirad, the position of the IP would have to be known to 6 millimeter in Z and to 0.6 millimeter in radius in order to have an uncertainty on the acceptance smaller than 10 to the -4. So this is quite easy to achieve But on the other hand, the distance between the two arms here should be known to 100 microns, so over a distance of 2 meters. And most challenging, the inner radius of the luminometer has to be known to an exquisite precision at the micron level, which means tight constraints on the mechanical assembly of the detector. Another measurement for which the control of the acceptance will be challenging is that of RL, the ratio of the Z widths into leptons and hadrons. So this observable allows precise measurements of the lepton couplings and is very sensitive to alpha S. So the FCC statistics would allow a measurement with a relative uncertainty of 3 times 10 to the minus 6. And experience from LEP shows that the geometric acceptance of the lepton pairs is a dominant systematics, and one would need to do 100 times better than LEP in order to beat it down to the level of the statistical error. So this is likely to require an asymmetric selection as described previously, which at LEP was only needed for the measurement of the luminosity, and again, a careful control of the boundaries. For example, for measuring the electron width, the innermost radius of the incl calorimeter should be known to a few microns, which poses constraints on the mechanical precision that will be easier to control with an hermetic calorimeter as opposed to a petal design. Now, of course, it is not all about acceptances. An excellent muon momentum resolution will be crucial at the z-pole, for example, for the determination of the z-widths, where the uncertainty is driven by the relative uncertainty of root S between the different energy points, hence by the relative calibration of the root S measurements. So this can be controlled in situ from the invariant mass distribution of dimuon events. Now, for a full silicon tracker, the momentum resolution in the range of interest is limited by material and leads to a mass resolution of 300 MeV, which is much larger than the root S energy spread. So, albeit not great, this would still allow the Z widths to be extracted with a systematics of 25 keV, but this uncertainty depending linearly on the dimuon mass resolution, an improvement is desirable as achieved with a lighter tracker in order to get closer to the statistical error. Another example is provided by the search for lepton favor violating decays of Z's into tau plus mu. So here the analysis strategy demands a clear tau decay in one hemisphere and a beam energy muon in the other in order to suppress the Z to tau tau background. So ideally, one would like a momentum resolution better than, say, half of the beam energy spread, so 5 times 10 to the minus 4, and a full silicon tracker, which offers a 10 times worse resolution than that, still allows to probe Z to tau mu branching ratios that are 6,000 times smaller than the current limit. But again, as the sensitivity improves linearly with the momentum resolution, the Z-pole run would clearly benefit from a light tracker with minimal multiple scattering for 45 GeV muons.
2 minutes.
Oops. So moving now to the vertexing performance, which is crucial for heavy flavor, one should anticipate very large improvements in the heavy quark electroweak observables or BRC, the asymmetries compared to LEP. With a progress in technology, beta gig efficiencies 3 times larger than at LEP can be considered, hence gains in statistics that are much larger than the luminosity increase. The ideal vertex detector for FCC, however, differs probably from the existing or planned ones, since it has to be precise and thin and consume low power and able to cope with a high bench crossing rate. So here as an example, the DKB to K star tau tau nicely illustrates the potential of FCC with a good vertex detector. As you know, lepton favor universality is challenged in the B to S transitions at LHCb, and B to S tau tau is a good discriminator between the models that may explain these deviations. And with these requirements here, on the primary, secondary, and tertiary vertex finding, more than 1,000 signal events will be reconstructed. You see the signal peak here, which is likely unique to FCC. Vertexing will also be important for tau physics, especially for measuring the tau lifetime. Currently, the best single measurement comes from Bell, from reconstructing the decay length in 3-prong decays. The dominant systematics was due to the alignment of the vertex detector, but was smaller than the statistical uncertainty. So at FCC, the statistical uncertainty will be tiny. and the relative alignment uncertainty will also decrease with increasing statistics. So the dominant systematics may be due to the overall radial scale of the vertex detector elements, which would be controlled at the level of 10 to the minus 4, hence a potential uncertainty of 0.03 femtoseconds, so 20 times better than the current average. And since FCC will also improve the branching ratios by a similar factor, this relation between the tau lifetime and its branching to electrons will allow a precise test of lepton universality, as a plot illustrating how the anticipated precision on these measurements here in yellow would compare with lepton universality prediction in red. A last word about vertexing and displaced vertices to stress the unique opportunity at Tera-Z to discover new particles that would have escaped detection so far because they are very weakly coupled, the FCC statistic being here the key. So as an example, right-handed neutrinos are very strongly motivated. They could be produced in Z decays and could then decay with a far detached vertex into a lepton and a boson. The plot on the right illustrates that FCC, the orange curves, would largely cover the uncovered part of the interesting phase space in white. Hence, the possibility to identify far detached vertices larger than 1 meter from the IP is highly desirable at the Z-pole. And just before concluding, some comments about particle ID. It would be extremely useful to separate pions from kaons in the range between 1 and 10 GeV. An example being provided by the BS to DS decay, which suffers from large backgrounds from DS pi, which cannot always be reduced sufficiently, even with excellent momentum or energy resolution. Hence, particle ID is necessary. Separation at higher momentum, for example, for tau physics, would be useful too. So candidate technologies have been reviewed, and as in this morning, the drift chamber of idea looks promising and may cover the whole range of interest. And for the other detector concept, no ideal solution exists yet, as it is not easy to cover the whole momentum range and at the same time comply with the space constraints of the experiment. So to conclude, we have seen the huge physical potential of FCC at the Z-pole with a gain of 1 to 2 orders of magnitude in precision for the electroweak observables and a unique sensitivity to new physics. We still have lots of work ahead of us on the front of systematics in order to design detectors and analysis and improve theoretical calculations as well, so that systematic uncertainties are commensurate with a statistical one. And to that goal, a first set of case studies has been identified in order to better quantify the requirements of the detectors that have that are set by this physics potential. This has been written up in a contribution to SNOMAS that you can find at this link. And I should add that while the machine baseline shown in the TDR has 2 interaction points, and optics exist that would allow 4 IPs, so 4 detector concepts should be considered. That's it. Thank you for your attention.
Thank you, Emmanuel. Now, are there any questions to this talk?
Hi, Emmanuel, here's Uta speaking. Very nice. I saw that for the gamma Z, you are focusing only on the muons, but the nice thing is, of course, we have this very clean leptonic states that we also have ZEE. And did you consider also to use the Z for the relative luminosity monitoring as we are doing this now in Atlas? Because this should be really great that you use your high Z statistics and you have the EE and the mu channel, and then you could beautifully monitor time dependencies, for instance.
Yeah, well, at the level of precision of 10 to the minus 4, that may not be easy. Also, the luminosity is the key for the super precise measurements of many electroweak parameters. So I think you want to measure that with a process that is independent of these electroweak parameters.
Oh, no, it's a monitoring. It's a monitoring, so you make a normalization. And then you can spot time-dependent effects, and it's independent of the Z cross-section. This is something extremely nice that we just really pursuing in Atlas, and where we get really cross-checks of the various luminometers.
To study the monitoring. Yeah. That's indeed something that could be done.
Yeah, I think this would be good, that you should consider this.
Thank you.
Okay, Thank you, Emmanuel. So now let's move on to the last talk before the coffee break. It's the talk by Alessandro Bravar about the development of sci-fi detectors for time and position measurements read out with silicon photomultipliers.
Yeah, good morning. And as introduced, my talk will be on scintillating fibers detectors. In particular, I'll focus on the development of the scintillating fiber detector for the mu3 experiment at PSI. So mu3, just in one word, is an experiment searching for a very rare muon decay, namely the neutrinoless muon decay to 3 electrons, which will be a charged lepton flavor violating decay. And for doing this kind of measurements, you need a very high intensity, because the rate is, I mean, the potential rate of this process are very low. So we have a muon beam, a surface muon beam, stopping on a hollow target, decaying 2 electrons, sometimes possibly to three electrons. The tracks are measured with silicon pixel detectors. However, as you can see here on left bottom, if the rate is too high, there will be plenty of tracks, and you cannot really say from which muon decay the tracks are coming. However, if you have a good timing resolution, you can assign a timestamp or a time label to each track, and you can really identify events containing, for instance, with a muon decay into 3 electrons. So we have the scintillating fiber detectors surrounding the target in a barrel fashion, an additional timing detector using scintillating tiles. Well, in principle, building a scintillating fiber detector is not too difficult. However, we have several external constraints which we have to impose on our detector. First of all, the detector has to be very, very thin. Why it has to be very, very thin is to reduce the material budget and not to spoil the momentum resolution of the experiment. Otherwise, we'll be killed by the combinatorial and other backgrounds. So we went with a choice of making a detector using 250 micron fibers, but only 3 staggered layers of fibers, which is roughly 600 to 700 micron thickness. However, even with this low thickness, we must be able to provide very high efficiencies of the order 95% or higher, with a time resolution better than 250 picoseconds, as we saw on the previous slide, for rejecting the combinatorial background and selecting the good tracks. Later, I will discuss about the efficiency. Why is not 100%? You say, well, with fibers we can get 100%, is because we are reading the fibers on both sides. So these are like 30 centimeter long ribbons. They are read out with silicon PM arrays on both sides. You put some cuts there on the amount of light that you detect, also a timing cut, and once these cuts are applied, the efficiency drops to 96 or 97%. And the other problem is the limited space. The limited space, we have really not a big space where to install the detector and all the components, electronics, etc. So these are the two challenges: the thickness of the detector and the limited space. So as I said, I mean, they'll be read out with silicon PM arrays, which has, each detector has 128 channels. They are column detectors with 250 micron pitch, and the readout in the end will be performed with a Mutrig ASIC, which is a dedicated chip for timing applications. So here we see a few more details on the mechanics of the detector. Everything sits on a cooling ring, which works as a support structure for our scintillating fibers. At the same time, is providing the cooling for the electronics and also the silicon PMs through a thermal contact between the cooling ring and all the metallic parts in the setup. Now, the interesting thing about this cooling ring has some pipes inside, and it was produced by a 3D printed aluminum technology. So it's a 3D printed object in aluminum, which we tested and has no leaks, etc. So it performs as expected. And here below we see an expanded view of the coupling of the silicon PM array, which is shown here, to the scintillating fibers with the spring loading and the electronics and the mechanical structure, which is attached to the cooling ring, and will also serve not only to cool the electronics, but also the silicon PMs. Now, how we produce the scintillating fiber ribbons? Well, we develop a technology in Geneva, which is essentially winding the fiber around this elongated rectangle. Actually, it's not a pure rectangle because it has a small bending. The fibers are filled in a U channel which is exactly 32.5 millimeter wide, so we can push in exactly 128 fibers. We make a first layer, then we put some glue. We wait for this glue to settle, and then the first layer serves us as a pattern for the following layers. This is different from other technologies where you start with an existing pattern and you build directly from there. And it's not automated, it's a manual procedure, but is rather fast. I mean, we spend more time preparing the glue than really making the ribbons. Well, here we see one ribbon, almost the final size, is transparent. There's another reason I didn't mention before, but we cannot use titanium dioxide to paint the fibers to improve the light yield and reduce the crosstalk, because the titanium is has a large Z, and therefore will be also spoiling the momentum resolution of the experiment. So we are working with a clear glue. Here we see a profile of the fiber ribbon, and here are some measurements. Namely, the effective pitch is about 255 microns, while the fiber diameter is 250 microns, and in vertical, the spacing is 230 microns between two fiber layers. Then a word about the silicon PM array. We are using the silicon PM arrays developed for the LHC-B. So it's a standard silicon PM detector, if you wish, except that the pixels of the detector are not all of them connected to the same anode, but rather they are split in columns, such that each column, such that this device provides also some spatial resolution or with a pitch of 250 microns. As you can see, all these detailed photos taken with a microscope of the detector itself is 32.5 millimeters wide. As I said, I mean, it has 128 channels. About the breakdown voltage is around 52.5 volts. And we see here the IV curves for each individual channel, and all of them are contained within few tenths of a volt. Actually, the multi-ASIC that we are going to use for the readout of these fibers allows also the fine-tuning of the high voltage of each channel. Now, the big thing, important thing, was the selection of the scintillating fibers. We made plenty of studies comparing essentially all the fibers, reasonable fibers on the market. The fibers from Kurarai, the SF78, the most popular fiber, then the SF81, the Bicron BCF12, and also there is a new scintillating molecule, the NOL11, which stands for nanostructure organosilicon luminophores, which provides better performances in terms of timing. However, it's not yet commercially available, and our baseline design at present is based on the SF78 fiber. So these are the manufacturer parameters, like the attenuation length and the decay time of the fiber. We measured all of them in dedicated measurements, also with radioactive sources, etc., especially for the measurement of the decay time of the fiber. So for us, what is important is the time performance and the light yield, because the number of fibers is rather limited. So here we see the attenuation measurements for different fibers. Clearly, the Kurarai, the SC78 and NOL11, they have the best performance. The worst is the fibers from Bicron. We also studied much in detail the attenuation length with an LED. Of course, for us, since the detector is rather short, like 30 centimeters, what is very important is what happens in the first 20, 30 centimeters. And indeed, we see a component which is quickly absorbed, and then a second component which is absorbed with a longer attenuation length. Most of the applications concentrates on this longer attenuation length, like the LHC-B sci-fi tracker, etc. And also the parameters given by the manufacturer typically corresponds to the long attenuation length, which of the order of a few meters. However, this component here, which is well, we can see from the spectral response of the fiber that this is the component at the shortest wavelength, is quickly absorbed, and the attenuation length for this short component, short wavelength component, is of the order only 30 centimeters. Well, we performed the sorry.
2 minutes.
Okay. We perform a waveform analysis as of the signals from the detectors using analog electronics and waveform digitizers. Well, the advantage of the waveform digitizer, really you see what happens to the signals, really the arrival time of each individual photon. Here we have a second photon, third photon arriving, etc. This allows us really to measure the decay time of the fiber. And we see the signal with a rather long, quick decay component and a long decay component. The long decay component comes from the large quenching resistor of the silicon PM. some performances. As I said, I mean, the light yield, we see here comparing different fibers and different number of layers. But what is most important for us is the time resolution. And the best time resolution we can achieve is using the NOL 11 fibers with a time resolution of about 200 picoseconds. Actually, what you see in the plot here is the time difference between left and right. So there are two independent measurements. If we combine these two measurements and we take the mean time of the measurement, then the time resolution will be 200 picoseconds. Well, the crosstalk, I have not much time to discuss it, but the problem is that the particles will not cross the detector at 90 degrees. They will cross the detector at an angle about 30 degrees because everything is in the magnetic field. So the sizes of the clusters will be larger, coming from the crosstalk first coming from the fibers which are crossed, the crosstalk between the fibers, and also the optical dispersion on the surface of the silicon PM. This plot here summarizes the performance of the fibers. Clearly said, I mean, the NOR 11 has the best performance. However, it's not commercially available yet. So our choice is for the Kurarai SCSF78 fiber with a time resolution around 250 picoseconds and an efficiency of 95% in our configuration. As I told you before, the efficiency really depends on how we select our events. First of all, the thresholds we apply on the silicon PM arrays. Since we have only few layers of fibers, this threshold is very, very low. Will be about 2 photoelectrons we'll be requiring on each side of the ribbons at least, with a timing cut of 5 sigmas on the time resolution. And when we combine all of them, these two parameters, we end up with a 95% efficiency, detection efficiency for our detector. To finish, the final readout of the detector will be performed with the MU3 ASICs, which is a dedicated chip for timing applications. Actually, MU3 means muon timing resolver with gigabit link. Contains 32 individual channels with 50 picosecond time beams and capable of transmitting data rates in excess of 1 megahertz per channel. So here we see a prototype board that we developed recently and we're using for testing the arrays. It's not yet the final size with 4 chips. We need 4 chips because we need 128 channels to read one silicon PM array in total. And the preliminary results using this electronics is consistent with the results that you obtain with the analog electronics. So we are on a good track. So to summarize, well, we developed the very thin scintillating fiber timing tracker with silicon PM readout. We made studies of different scintillating fiber materials, and we select the SCSF78 fiber from Kurarai. The detector is very, very thin, of the order 700 microns, which corresponds only to 2 per mil of the radiation length, which is sufficient to obtain a time resolution of the order of 200 picoseconds on the mean time and efficiency in excess of 95%, with a spatial resolution about 100 microns, which I have not discussed, but also this is a bonus which comes from this detector. Now, the construction will be completed by the end of this year, and the commissioning will happen next year. We picked up some delays because of the problems that we all experienced this spring. And to finish, this is the team, is essentially the Swiss Institutes of Geneva, Zurich, ETH, and PSI working on this detector. And essentially the work is carried out mainly by students, by our PhD students. So thank you for your attention.
Thank you, Alessandro. Are there any questions to this talk? I don't see any questions or hear any questions. I will just ask, you're studying a rare process, you need a lot of statistics, and you need to handle a very large data rate. So actually, how much data do you produce, and do you plan to process it online FPGAs?
We didn't talk about it, but yes, we expect to produce, well, first of all, we have no trigger. It will be a triggerless experiment, so we'll transfer all the data through FPGAs, and where first processing will happen, and GPUs. And we are talking about a bandwidth in excess of a terabits to transfer all this data, not so much from the fibers, but from the silicon pixels, where we are talking about 200 million pixels. So this will go to FPGA boards with the ARIA 5, then a switch board using an ARIA 10, which will deliver all the data to our computer farms with GPUs. And the idea is to filter online this data as they arrive and store only events containing 2 or more track candidates. So all the simple muon decays of muon decay into an electron will be rejected at the filtering stage, at the online processing stage.
Okay, thank you very much, Alessandro. Now, if you don't object, everybody please unblock your video and let's make a group picture. How do I look like? Yeah. Jana, are you online? Gallery view. One of two. Is there a way how to have all the pictures in the same? Yes. So I will try to make a print screen. Save as. And let's move to the screen. Okay, thank you. So now let's have a coffee break until 10:45, by which time the Mitesh will take on the chairing of the session. So thank you and enjoy your coffee. So Mitesh, do you have any questions?
No, I hope it will go smoothly.
Okay, so we are missing slides still from Takuya Tashiro. I wrote him email very early this morning, so he still didn't upload his slides. So I think we can skip him and have him at the end if he manages to upload.
Okay.
Hello, can you hear me?
Yeah. Sure.
Yes, I'm Takuya Tashiro, and I have a trouble on uploading, and I sent an email to the
Scientific Secretariat?
Yes, but I have not yet received the response.
Okay, so I will write an email to upload your slides, and if not, just play them from your computer, okay? Because otherwise I see all the slides, yeah. Upset Takuya. So I did just send the email to the Scientific Secretariat. They usually react very quickly.
Thank you. And is it possible to upload by you? If it is the case, I will send my slides to you.
Yeah, so if you can just resend them to the secretariat.
Okay.
I think the problem is if you have more email addresses registered in Indico. So that is usually the problem. So, but you can play them now from your computer, and then they will upload it. Because I don't have the right to. I'm not the supreme manager, so I cannot mess with the Indico.
The way I had to do this for myself was actually to add to my CERN profile the address that was used for the registration at HL.
Yes, this is the way.
And this worked.
Now I succeeded in uploading my slide.
Okay, perfect.
Okay.
So I think, Mitesh, you can start.
Okay, so let's get going. Do you hear me?
Loud and clear.
Very good. All right, so our first speaker, Takuya, is going to talk about the preparation of large aperture photon detectors for Hyper-K. So if you would share your slides, then we can get started.
Okay, thank you. So I will share my slide.
Great.
See my slide?
I can't yet, but
oh, okay.
Michael, is it just me? Do you see them?
I don't see the slides. There is this green button on the bottom which says share screen, and then you should select either application or desktop.
So I'm sorry.
Or maybe Mitesh, can you try sharing the slides?
Sorry, could you do it? Thank you.
Yes, okay, give me a second.
Yeah, I see them. If we can try to have them full screen.
Yeah, one sec. Okay, does it work now, full screen?
Yes.
Yes.
Good. Okay, so.
Okay, thank you very much. And I'm sorry for the trouble. And I will start the presentation of preparation of large aperture photodetectors for the hyperchemical detector on behalf of the hyperchemical plot collaboration. Could you go to slide number 2? Thank you. And I will have a brief introduction of hyperchemical detector. Hyperchemical or HyperK is the third generation water chain detector in Kamioka, Japan. The first generation is Kamiokande, whose total mass is 3 kiloton and whose initial mass is 2.1 kiloton, which detected supernova neutrinos for the first time in the world. And the second detector is the Super Kamiokande, which is under operation now and whose total mass is 50 kiloton and initial mass is 22.5 kiloton, who discovered the neutrino section. And the third is my topic, the hyperchemical, which is planned to start in 2027, and the total mass is increased to about 260 kiloton, and initial mass is 188 kiloton. It is designed to study several physics topics, including nucleon decay, CP variation in lepton sector, and neutrino astronomy, and so on. And finally, the construction is detected to start this year. Okay, and please go next. Thank you. And hyperchemical is one of the water Cherenkov detectors. And in water Cherenkov detectors, the charged particles passing through the water are identified using the Cherenkov light limited and detected by the photodetectors attached to the walls. And since the Cherenkov ring pattern is different among particles, the PR is performed based on the pattern of rings. These plots are the examples of hyperchemical simulation. Since the electron water Cherenkov lights showered, so the electron links becomes like the left plots, and while muon links does not emit showering, so the muon links become like right-hand plots. So the difference of Cherenkov link pattern is important in identifying the particle IDs. And please go to the next slide. Okay, and so in order to do that kind of things, photodetectors are used in hyperchemical detectors. And the large aperture photomultiplier tubes or PMTs are used in hyperchemical. Several types of PMTs are considered. The first candidate is box and line PMTs, whose diameter is about 20 inches. And in the past, about 100 PMTs were installed into SuperK in order to evaluate the performance. And we also consider MCP PMTs, which was ordinarily developed for Juno, but it is also improvement. Improvement has been studied in order to be suitable for hyperchem. And we also consider multiple PMTs. Multiple PMTs have multiple 3-inch PMTs stored in 20-inch case, and it will be discussed in a dedicated talk by Gianfranca today. And mass production is 20-inch PMTs is scheduled to start this year. Let's go to the next slide. And until now, the preparation of 20-inch PMTs are ongoing. The it includes the development of high-quality PMTs, and high quality means high detection efficiency, good charge and timing resolution, low dark noise rate, tolerance to water pressure, and so on. And also, we have evaluated the performance of prototype and test PMTs using many systems, and preparation of covers are also important. And the covers are required to be tolerant to hyperchemical water pressure and shock of PMT implosion. Also, we have been developed the support structure and iteration method. Please go to next. Okay, so I will talk about the box and line PMTs, one of the candidate 20 PMTs. And the box and line PMT was developed for hyperchemical by Hamamatsu Photonics company. And it is designed to have larger detection efficiency, time resolution, and charge resolution compared to superchemical PMTs. And one of the main improvement is the dynode structure, box and line structure as right-hand plot. And it was the performance was measured in water as it was installed into superchemical in 2018, and the measured performance includes the detection efficiency, charge resolution, and timing resolution. Please go to next. Okay, the detection efficiency was measured using the calibration system of a nickel carbonium source. This system is actually the system used in superchemical. And the number of photons detected by hyperchemical is approximately 1.97 times larger than superchemical in average. The bottom plots show the distribution of relative detection efficiency compared to superchemical detector and superchemical PMTs. And the x-axis is the relative detection efficiency normalized by the average superchemical PMTs. So as you can see, the relative detection efficiency in box and line PMTs is approximately 2.0. So this improvement was achieved as a result of both higher quantum and correction efficiency. Please go to next. Okay, so and we measured the charge resolution using the calibration system of laser diode. The resolution, the bottom plot is the resolution of sigma over mean of charge resolution plot. In SKPMTs, the sigma over mean is about 54% in average, while in box and line PMTs, it is about 27%. So it means the resolution of box and line PMTs is about twice better compared to the SKPMTs. Please go to the next. Okay, and about the timing resolution. The timing resolution was measured using the calibration system of laser diode as well. And the bottom plot is the transition time spread distribution of box and line and SKPMTs. And clearly the box and line PMTs have better performance compared to SKPMTs, as in SKPMTs, the average transition time spread is about 2.95 nanosecond, and while in hyperchemical box and line PMTs, it is about 1.50 nanosecond in average. So the performance of timing resolution is about twice compared to the SKPMTs. And the next topic is, please go to the next. The next topic is PMT dark noise. The dark noise is one of the very important parameter of PMTs in HyperK, because the dark noise can affect the reconstruction, especially in low energy events. This plot is an example of hyperchemical simulation. The dashed and solid line corresponds to the dark noise of 8.4 kHz and 4.2 kHz. And the blue, green, and black line corresponds to the 20%, 30%, and 40% photo coverage. And for example, when we choose the 20% photo coverage, the Vertex resolution is about 130 centimeter if the electron energy is 5 MeV, and it can be as well as 150 centimeter if the dark noise is about 8.4 kilohertz. So the resolution is better. The better resolution can be achieved if we can achieve the lower dark noise. So the goal of the hyperchemical PMT's dark noise rate is about 4 kilohertz. Please go to the next slide. Sorry, please, the page 11. Yes, thank you. And for this reason, we have been trying to reduce the dark noise. And in the past study, we found that the significant amount of dark noise was triggered by continuous pulses, the pulses that appear continuously within short time or an order of about 10 microseconds. And this plot is one of the example of continuous pulses. As you can see, multiple pulses are observed within about 10 microseconds. So we found that this contributed to the dark light noise a lot. So, and one of the sources of continuous pulses is scintillation light triggered by decay of radioisotope contamination in the PMT bulbs. So we reduced the RY contamination to reduce the dark noise last year. Please go to next. So for this reason, we improved the glasses by reducing the contamination. And the contamination of uran and tritium has been successfully reduced to about half in new PMTs last year. And in new PMTs, the uran contamination is about 10.9, while it was about 5.4 in the old glasses. And it's in tritium, the contamination is as low as 0.95 becquerel per kilogram, while it was about 1.8 in hyperchemical old PMTs. And in the calium-40 contamination, it is not reduced compared to the old PMT, old glasses, but it is much reduced compared to the LHeC PMTs. And this improvement resulted in significant reduction of dark noise. As in the old glasses, the box underline PMT's dark noise was about 6.6 kilohertz in average, and the PMTs with low RY glasses, it was reduced to as low as 4 kilohertz in average. Please go to next. And the second candidate, MCP PMTs, were also measured in Kamioka Mine laboratory. And these plots are the performance of counting resolution and time resolution. In the counting resolution, it is about 40.3%, and in the timing resolution, it is about 1.8 or 1.9 nanosecond in sigma. These are both better compared to the LHeC PMTs, whereas the time charge resolution of LHeC PMT is 54% and timing resolution of LHeC PMT is about 3.0 nanosecond in sigma. And please go to next. And the tolerance to water pressure was also measured in water, and the water pressure of 1.2 megapascal corresponding to 120 meter in water depth is proved to not to damage the PMT. So it can be used in the water depths of hyperchemical. Please go to next. And we are also preparing the PMT covers. PMTs will be stored in covers to avoid chain implosion. And several designs are being prepared. The left-hand design was designed by Spanish contribution, and the right-hand design was designed by Japanese contribution. And the PMT covers must be tolerant to the implosion. and must be proved to avoid the implosion chain. And the right hand design was already proved to work in hyperkamikane as implosion test was done. And in the left design, the implosion test is not yet done, but it is scheduled to be done next year. And please go next. Thank you. And the design of PMT support.
You're about to run out of time.
Okay, thank you. And the design of PMT support structure is ongoing as well. Mock-up system of the PMT support structure was built in ICRR last year, and the design of PMT support structure and installation method are ongoing, being studied to realize efficient and precise installation. The next page, please. This is the summary. Okay, the new PMTs for hyperkamikane experiment are being prepared, and the box and PMTs are MCP PMTs were measured and developed for hyperkamikane. So the performance of new PMTs was evaluated and proved to show better performance than SK PMTs. Especially box and PMTs were installed into SK in the evaluation. The dark noise rate of box and PMT was reduced to about 4 kHz, finally achieved our goal. And the preparation of covers and installation system are ongoing as well. And the implosion test of Spanish cover is scheduled for cover evaluation, and the installation is being studied using mock-up system. Okay, that's all from my side. Thank you for listening.
Thanks very much. Are there any questions? Please put your hand up. Okay, I don't see any, so maybe I can quickly ask, what have Hamamatsu done to improve the quantum efficiency? Do you know?
They improved. One of the improvement is the dynode structure shown in page 6, and the photocathode was improved as well in order to increase the detection efficiency, increase the quantum efficiency.
Very good.
And yeah, thank you.
Okay, thanks a lot. Okay, so let's thank the speaker and move on to the next contribution, which I think is Gianfranco on a multi-PMT photodetector system for HK again. So Gianfranca,
can you see my screen?
I can see your screen. Please go to full screen and get started.
Sorry.
No, it's okay. I think it's bottom left. Or...
Okay. Okay, now it's working. Okay. Thank you for inviting me to this conference. Hello, everybody. I will discuss on multi-PMT photodetection system for hyperkamikane experiment. Hyperkamikane is a next generation underground water Cherenkov detector for neutrino observation. In particular, HyperK will observe neutrino produced at J-part accelerator complex to investigate leptonics CP violation. Details on HyperK physics capability have been already discussed at this conference. In HyperK, we have a far detector, a far water Cherenkov detector with a fiducial volume about 8 times larger than superkamikane ones. And this detector is currently under construction. A system of near detectors will monitor the neutrino beam for the accelerator neutrino part. A new water Cherenkov detector in particular that is named the intermediate water Cherenkov detector will be realized to control the systematic uncertainties. Details on near detector system have been discussed in a separate talk. The operation will begin in 2027. The inner part of the water Cherenkov detectors will be instrumented with the new technology photosensor for faster and with higher efficiency and compared with the Super Kamiokande ones, with wide dynamic range, high time and charge resolution, and high detection efficiency. In the far detector, the baseline design see the use of new high quantum efficiency 20-inch voxel line PMTs. Also 20-inch MCP PMTs are considered as an option, as discussed by Tashiro-san in the previous talk. A hybrid design with the use of 20-inch PMTs and the system of small PMT, the multi-PMT system as proposed by ChemTriNet collaboration is also considered for HyperK. In particular, in the far detector, we consider the hybrid design with the part of 20-inch PMTs and part of multi-PMT, while for the intermediate or Cherenkov detector, the multi-PMT will be adopted as a photo detection system. In the multi-PMT system, photosensors and electronics are arranged inside the pressure vessel. The resulting segmentation of the sensitive area features several attractive advantages compared to the single PMT concept. In particular, the directionality, the increased granularity improve the event reconstruction capability, in particular for multi-ring events. An hybrid design with 20-inch PMTs and multi-PMTs considered in the far detector, while multi-PMT will be used in the intermediate, as I said before. The outer part of the detector acts mainly as a veto for entering particle and is observed by the system of PMTs as discussion by Stephane in the later talk. In HyperK, the multi-PMT system is based on the use of 19-inch PMTs arranged with the relative electronics in the pressure vessel, with an acrylic dome and a PVC cylinder to cover the PMT and electronic system. The resulting segmentation of sensitive area give us a possibility to explore a superior photo counting capability, the improved angular acceptance, the extension of dynamic range, and the possibility to check for local coincidence will allow us to improve reconstruction capability. Preliminary results based on the far detector simulation studies demonstrate that the vertex and angular resolution are better, in particular for low energy events. And at high energy, muons and electron separation is improved, in particular near the wall. And in general, the improvements are significant at the edge of fiducial volume. Several configurations have been studied with a different number of multi-PMTs. The improvement with multi-PMT is clear with the use of already 3,000 multi-PMTs and improve adding more and more multi-PMT. In simulation studies for the intermediate water Cherenkov detector has been already discussed by Nick Proust at this conference in other talk. A huge R&D activity is ongoing to optimize the multi-PMT for HyperK. Several studies to improve the mechanical design are ongoing, in particular to resist at the high pressure in the HyperK detector and for long-term operation in water. For the acrylic dome, optical, mechanical, and studies on measurement on radioactivity contamination have been performed. Then tests on water penetration are ongoing. More and more tests have been planned to realize a final design for application in HyperK. In particular, radioactivity contamination will be measured for all the multi-PMT components. and the multi-PMT prototype are fully characterized in air and in water. Menfino water tank in French is used for the preliminary measurement in water, but a general test experiment to fully characterize the multi-PMT performances is planned at CERN. Several prototypes for HyperK have been realized until now. In particular, we have the multi-PMT pressure prototype that show that the acrylic vessel resists to about 1.8 megapascal. Another prototype realized at Triumph tested the full geometry with the cylinder, and also for this test the results are encouraging. Another prototype to test the multi-PMT electronics has been realized, then it's already in data taking at Menfino setup. The optical prototype is realized to check the optical coupling between the parts of the multi-PMT, and the test, the measurements are ongoing. The multi-PMT performance are strictly related to the ones of 3-inch PMT used for it. Several manufacturers, as Hamamatsu, AT Enterprise, and HL-LHC, developed similar 3-inch PMTs. At the moment, most effort have been focused on Hamamatsu and HL-LHC PMTs because of their better performances. PMTs have been fully characterized in terms of gain, peak-to-valley ratio, and TTS, using both positive and negative high voltage. Charge resolution of Hamamatsu and HL-LHC 3-inch PMT are similar, but the time resolution offered by Hamamatsu PMTs currently significantly better than the HL-LHC ones. For what concern the PMT dark rate, the PMT dark rate count affects the multi-PMT reconstruction capability, especially at low energy. So based on simulation study, the best performance in HyperK are obtained with a PMT dark rate of about 100 Hz. But currently, the commercially available 3-inch PMT show a bad, not to fulfill this requirement. In particular, Hamamatsu typical dark rate is about 200-300 Hz, while HL-LHC is now going to improve the performance of their PMTs. Several strategies are under study to improve the dark counts, in particular add dielectric material to insulate the PMT surface and reduce the probability of accidental discharge, adopt a conformal coating as in ChemoTriNet experiment, reduce the continuous pulses that are mainly related to decontamination in the glass of the PMT, and we started the R&D with the manufacturer to reduce the radioactivity material and improve the PMT dark rate. We plan to conduct a series of tests to decide also on the treatment of the PMTs and the preferred polarity. For what concerns the high voltage, to cope with the power consumption restriction in HyperK, in particular detector in particular, a basic comfort voltage multiplier has been designed for both negative and positive high voltage. Negative high voltage has been tested in complete configuration of the multi-PMT, showing a very stable high voltage with the power consumption 3.1 milliwatt per channel at 1.5 kilovolt. For the full multi-PMT with 19 PMT, we will have about 60 milliwatt for the high voltage part. For the positive high voltage board has been also realized with the same input and output control of the negative high voltage board. This is currently under test at NFN. The best solution will be used for the that will guarantee the reduced dark rate will be adopted. The requirement for the readout are a timing resolution of about 500 picosecond for 1 P, while for a better timing resolution of about 100-200 picoseconds is required for large photoelectron pulses. The charge resolution of about 0.25 P up 25 photoelectron is required, and the power consumption for the far detector, HL-LHC detector, is very constrained, driven by water separation requirement, while for the intermediate water Cherenkov detector, this requirement is not so strong. Instead, the capability to distinguish between different hits in different neutrino bunches required for the intermediate far detector, intermediate water Cherenkov detector. So different digitization is considered for the far and intermediate detector. A QT digitization based on a discrete component will be adopted in the far detector, while a FADC digitization with onboard signal processing will be used in the intermediate water Cherenkov detector. For the far detector, a sample and hold plus a DC based on discrete components has been adopted. We have a single channel electronics with the high voltage at the front end board, and the main board that will merge the single channel outputs and process the information. The acquired data are transmitted out of the multi-PMT with a single Ethernet cable that give also the power supply, the clock, and the trigger to the multi-PMT. For what concerns the front-end board, this is integrated with the high voltage board and is characterized by a power consumption of 40.5 milliwatt per channel. So the total power consumption, the main board is based on the use of a single board computer Linux, and has also some sensor for pressure and temperature and humidity monitoring. The total power consumption for the multi-PMT is about 4 watt. For the intermediate water Cherenkov detector, the digitalization relies on waveform sampling using fast analog to digital converters with the time and charge estimation done in the FPGA. Sorry. The ADC, the FPGA controlling the ADC to preserve timing resolution and pulse separation with no dead time. A single Ethernet cable will provide the power and then the communication outside the multi-PMT vessel. Based on a review of commercially available ADC, a 125 SPS system with a sampling period of 8 nanoseconds and the resolution of 12 bits has been considered. The expected time resolution of the readout system at various resolution of the FDC and for varying number of photoelectrons, namely at a different level of SNR, have been estimated. The results in the pulse shape, the results of LTS, LT SPICE simulation of the implemented circuit is shown. The resulting pulse shape at the output of the filter is bipolar and has a total width of about 97 nanosecond, as shown in the plot. A system collect, sorry?
I'm sorry, your time is already elapsed. Can you wrap up?
Okay, sorry. All the system, the information between from 24 different multi-PMT will be arranged with the multi-MT concentrator CALD. And in summary, we can say that hypercamiocande is officially approved in Japan and is under construction, will begin operation in 2027. Multi-PMT are considered considered as an option in the far detector. It will be used in the intermediate detector. Preliminary studies show that adding multi-PMT improve hyper-K physics capability. The international R&D is actively ongoing to optimize the multi-PMT design and performance. New collaborators are welcome to contribute to the detector and physics program. Thank you.
Thanks very much. Okay, any questions for Gianfranca? I see one from Jilei Xu. Please go ahead.
Yeah, hello, thank you. I have a simple question about, yeah, it's interesting to put many PMTs, 19, right? PMTs together and like chemistry night. And what's the size for one prototype? PMT prototype is almost equal to the 20-inch PMT?
Yes, the idea is to have the same system also for the PMT support inside the tank. So the design of the multi-PMT will match the dimension of the 20-inch PMTs, so the same diameter.
Okay, thank you. And another question is, it's interesting, you put some metal around the PMTs to want to collect more light. It will influence the TTS, right? Or no? Maybe page the last page 7 or
7.
Yeah. Yeah. For the left plot, is you put some like a height to around the PMTs. It will influence the PMTs TTS parameter.
I don't know this point. We are now starting with the test of the system. The idea is also have inside the multi-PMT calibration system. So we are going to work a lot on the optimization of the full system, both in the mechanical and the sensors inside the PMT. The main problem in the multi-PMT for hyper-K is the dark count of the PMTs. So we are now mainly focused on the reduction of dark rate.
Okay, so I think
sorry.
We should probably pull the discussion up there. Thanks again to Gianfranca. And I know the next speaker is here because it's...
Thank you.
Thanks a lot. So Julie, are you able to share your slides?
Yeah. Wait.
And you will talk about status and progress of the Juno detector, if I understand correctly. So please.
Okay. Can you hear me and see my screen?
I can hear you and I can see your screen.
Okay.
If you would make it full screen, that would be great.
Yes. Wait. I don't know why it is. Okay.
Very good. Okay, go ahead.
Okay, my name is Jilei. On behalf of Juno Collaboration, and I will introduce about Juno detector's status and progress. And first, I will briefly introduce the Juno detectors and phase prospects, and then we introduce the sub-detectors and status in detail and summary. Juno is the German underground neutrino observatory. The target is about 20 kiloton liquid scintillator and with energy resolution 3%. And now it is under construction in south of China. You can see this map. This is Hong Kong, and it's near Hong Kong. And this is Juno site, and about 53 kilometers from the 2 nuclear power plants. And it's put in the neutrino isolation maximum site. And so the main goal is for Juno is to determine the neutrino mass ordering by reactor anti-neutrino. It means to determine the red curve or the blue curve. And so this requires the detector should be with a high transparency liquid scintillator and a high coverage of PMTs and a low background. So it's the most challenging design in reactor neutrino experiment. And also Juno have a multi-purpose For example, it can measure solar neutrino oscillation parameters with the highest precision, and also can detect many neutrinos like solar neutrino, supernova neutrino, and geoneutrinos, and also have a certain ability to test the proton decay. And the left upper plot, you can see this is a Juno surface scenario real picture on the ground surface this summer. And about 700 meters below is our real Juno site. Now we are digging, the tunnel is already, and we are digging the experiment hall and also the water pool here. And this slide shows the cartoon picture of Juno detectors, and about 20 kiloton liquid scintillator was filled in the acrylic sphere, and about 18,000 20-inch PMTs and more than 25,000 3-inch PMTs around the target. And we call this system is a central detector. And the central detector will be immersed in the water pool, and water pool is the vital detector. And at the top, we have the top tracker to track muons. And now Juno have 77 members and about 600 collaborators. And this picture shows the 16th Juno collaboration meeting in this July. And here comes the acrylic spherical vessel and the stainless structure. Juno will build the largest acrylic spherical vessel. So how to achieve this? For Juno on-site building, it will be divided by many pieces. So this size is typically one piece, and then it will be bonding together. Now for each piece, it will be supported by the supported bar on the stainless steel structure. Currently solved all the technical problems like the high precision curved sheets, the anti-seismic, and the transparency, and the low background, and the fast bonding, and annealing. Now currently it's in production. You can see this picture is pre-assembly in the factory, and this is the bonding test for acrylic. And Juno also will produce the high transparency liquid scintillator, maybe the highest possible light years, and with a low radioactivity for Juno. And this is materials of the liquid scintillator, and we will achieve 10 to minus 15 gram per gram for the reactor antineutrino. And we also use packed to, we can achieve 10 to minus 17 for solar neutrino. To achieve this, we built the purification systems. Currently, a pilot liquid scintillator purification system built at the Tanabe experiment for R&D. And in this year and the next year, we built the purification system on the Juno on-site. And like the aluminum filtration and distillation and steam stripping and water extraction. And then the liquid scintillator will be piped down to the experiment hall. And in the experiment hall, we also have the online circulation purification system. And the highlight is we also will build the OSRIS. It means the online scintillator internal radioactivity investigation system. And this system is can have the sensitivity of 10 to minus 15 gram per gram per day. And here is the 20-inch PMTs. Juno needs the coverage larger than 75%. How to achieve this? It needs the 20-inch PMTs closed packed on the surface. It's like this. Totally we have the 18,000 and about have the 13,000 macro channel PMTs from NVT company, And for the previous HyperK slides, also introduced it. And also we have 5,000 download PMTs. And currently, almost all the bare PMT are delivered and accepted. Test going well. These two plots is you can see the test result. And the highlight is currently the MCP PMTs, the new production will be high quantum efficiency, it's larger than 30% for the photon detector efficiency. And this picture shows the porting for Hamamatsu PMT, and porting is goes well. This shows the MCP PMT, and this shows the design of the implosion protection cover. And now it is started the production. And for 3-inch PMTs is Juno we installed the more than 25 kilo 3-inch PMTs will be inserted in the gaps of the large PMT. And it's from the HDC photonics, and it can make double calorimetry to calibrate the non-uniformity and non-linearity for large PMT, and also can increase the optical coverage, and also can extend the energy measurement for muon physics, and also can independent system for supernova and solar neutrino parameters measurement. So there's many advantages. So now currently is in good progress. All the PMTs are produced and delivered, and for the other systems are going well. Juno also will have the comprehensive calibration system, because we not only have the one-dimension calibration unit, and also have a two-dimension is the cable loop system, and also at the boundary of the sphere is have a guide tube, and also have a three-dimension. It's a remotely operated vehicle. It will swimming in the liquid scintillator and can reach anywhere. And also have the auxiliary system like the ultrasonic sensor and the CCD, and for the others to monitor the liquid scintillator. So after calibration, we will achieve the nonlinearity, and bias will be less than 1%. And so for the effective energy resolution is pegged to be less than 3%, between 1 MeV to 8 MeV. So for the veto system is water pool and the top tracker. For water pool, we have 35 kiloton ultra pure water to passive and active to shading the rock neutrons and radioactivity, and also can tag muons. And also we have the more than 2,000 20-inch PMTs on the CD surface, but it towards the other side. And the PMTs will be in the Earth magnetic shading coils. And this coil can realize the residual magnet less than 10% of local Earth magnetic field for CD PMT, and for veto PMT is less than 20%. And also for the we have the high density PE lining to prevent the rhythm from rocks and also keep the water clean. And we also have the water circulation system in good shape now for the calculation. And for the TAVIC, it will be cover the CD and water pool and in good quality and technology from Tabe. And for top tracker, we will reuse the target tracker wall of the Opera experiment. And we built the 3 layers XY plastic scintillator. Now it's the Juno on-site, waiting to installation. And for the electronics is going well. And for the top tracker, it's not only for veto, but also for the muon tracking validation. For the Juno Tau is Taishan anti-neutrino observatory. It's a 10-level high energy resolution liquid scintillator detector about 30 meters from one of the Taishan reactor core. It's a satellite experiment of Juno. And now you can see the CDR online, it is measure the reactor neutrino spectrum with sub-percent energy resolution larger than 2 or 3 MeVs. Then we can got the model independent reference spectrum for Juno and a benchmark for the investigation of the nuclear database. And for detect design is here. The highlight is will be almost a full cover of the detector with the silicon PM, and we'll be working in the -15 degrees C. And for each day we got 2,000 reactor neutrinos, and we start operation in 2002. And summary is for Juno is a multi-purpose experiment, not only for mass ordering but also for the solar oscillation parameters, and also can detect many neutrinos, and also have ability to detect nucleon decay, etc. And currently the detector component production is in good progress, and we start the data taking in 2022. So here is the related talks, and this is the neutrino session by Cesar, and for others and the posters you can see.
Thanks very much.
Thank you. That's all.
Good. Are there questions?
Mm-hmm.
Put your hands up if there are. I can't see any, so maybe I will try and ask one. So I just wanted to go back to your slide 3 about the design of this experiment.
Mm-hmm.
This plot on the kind of center lower part of the slide.
Mm-hmm.
So does the vertical axis take into account the loss in flux from being further away?
Sorry, what's the losses?
So as you go, presumably as you go further away from the source of your neutrinos, you spread out the beam to some extent. Is that taken into account? Or this is more number of observed over expected as a function of distance?
This observed divided by is expected. For expected there is no oscillations.
Right, but have you taken into account the geometric or the loss in geometric efficiency from being further away?
You mean the here one, right?
Right. So as you move further away, you decrease the number of events you observe, regardless.
Because it's also oscillated because we to observe the antineutrino disappearance. You know, the antineutrino comes from the reactor, and then after 53 kilometers, it will be part of the antineutrino becomes to the mu neutrino or the tau neutrino. So we only can detect the electron neutrino, anti-electron neutrino. Yeah.
Thanks very much.
Some disappearance.
Okay, so thanks again.
Thank you.
Let's move on. So next we have Patrick Dunne on the status of the June near detector. Patrick, are you there?
Yes. Can you hear me?
I can hear you well, and I can start to see your desktop. Now I see your slides. Please go ahead.
Perfect. Okay, so as Mitesh says, I'm going to take you through the status of the June near detector on behalf of the June collaboration. So I'll start with a brief introduction to June, and I should say as I do that I'm focusing today on June's oscillation program, but June has large beyond the standard model and supernova physics programs as well, and you can see talks on that and several other aspects of June from these other individuals at this conference. So going back to that focus on the oscillation program, after I've introduced you to the sort of overall concept of June, I'll take you through what the requirements are for the near detector within the June experiment. and then go through the conceptual design report reference design that we've come up with for June's near detector, and let you know how each component of the reference design is specifically targeted to meet these requirements. So June is a long baseline neutrino experiment with a 1,300 kilometer baseline. What that means is that we create a wideband high-power neutrino beam at Fermilab. Our particular beam has neutrino energies in around the giga-electron volt range, and it has a power greater than 1 megawatt, so a very, very high-power beam. We fire that beam, the 1,300 kilometers, to the Sanford Underground Research Facility, where there will be 4 10 kiloton fiducial mass liquid argon fire detector modules. What I'm going to focus on today, however, is the near detector, which sits 575 meters from the neutrino production source. So that the main function of this is to constrain the beam before oscillations have taken place. And just kind of going back to that overview, the flagship physics topics of June are searching for electronic CP violation and precision measurements of it if we discover it, the neutrino mass ordering, and precision measurements of theta 2.3 and delta M squared 3.2. So moving on to the requirements of the near detector, the main requirement is to predict the spectrum that you expect at the far detector, both with and without oscillations. So to give you a rough idea of what we're looking for, the 2 main effects in the oscillation physics program are the disappearance of the muon neutrinos that we created. So you can see here on the left-hand side, the dashed spectrum is the unoscillated spectrum, and the black spectrum is the oscillated spectrum that we expect. You can see here one of the main strengths of June, that we have a wideband beam, so we can really map out this whole oscillogram behavior. And then on the right-hand side, you can see the other thing that we mainly look for, which is the appearance of electron neutrinos. So on this case, the solid line is the oscillated spectrum if there's no CP violation, and the 2 dashed lines are the spectrum expected if CP violation is maximal in the 2 directions. So that gives you an idea of the scale for the uncertainty that we need to be able to distinguish between these 2 and make a precision measurement. The elements that really go into predicting these numbers of events that we see are the neutrino flux, so how many neutrinos did you fire at your detector, the neutrino interaction cross-section, how likely they are to interact, the detector efficiency, how likely you are to see those interactions, and then the oscillation probability, how many of them have oscillated into the flavor that you expect to see. So breaking the requirements down a bit more to predict the spectrum at the far detector, what we really need to do is constrain each of those individual elements. And an important thing to remember there is that they're not just individual numbers. I mentioned that one big strength of June is that we have a broadband neutrino spectrum, but that means that the flux is quite wide and is a function of the neutrino energy. So we need to measure that neutrino flux sort of in that full sort of spectrum. And also we need to measure it as a function of time. So that's something previous experiments have seen, that you can have problems with your neutrino beam system that happen sort of in a time-dependent way, and you need to be able to sort of isolate that from your sort of overall measurement of the number of interactions over the course of the whole run. The second element, that neutrino cross-section, is again a function of the incoming neutrino energy, but it's also a function of the particular type of neutrino interaction that occurs. And there are many different final states that can be created from neutrinos. So instead of constraining just the number for the cross-section, we talk about constraining the cross-section model as the requirement that we have for our near detector. The next bit is the detector efficiency. So detector efficiency is also a function of the particular final state that comes out. We're going to have lots of different types of particles, and we need to make sure we can constrain all of those. But also, the near detector is going to operate in a very different environment to the far detector. So being much closer to the beam production point, the rate at the near detector will be much, much higher. So we need to make sure that the near detector can operate in that environment. This aspect and the fact that we want to really pin down all of these other elements means that the detector technologies that we use won't necessarily be identical to the far detector. So we need to know how to make the transfer of those measurements to the far detector. And that's another key requirement. The last high-level requirement that we have is really related to unpicking the interdependence between these 3 different components. And what that requirement is that we be able to take measurements with different fluxes. So if you can change only one of these independently of changing the others, that gives you a good indication that you're better able to sort of work out that that change that you saw really was due to just a different flux and not due to a cross-section effect. And that helps you get a better picture of which effects are coming from which piece. So moving on now to the CDR reference design. The reference design has 3 components, with the neutrino beam coming in on the right here. 2 of these components, the 2 most upstream, are able to move perpendicular to the beam axis, giving access to different fluxes. So that's that requirement ticked off. And sort of going from the most upstream point downstream, the 3 systems that we have are ND-LAR, which is a liquid argon TPC with optically isolated modular and pixelated readout. ND-GAR, which is a high pressure gas time projection chamber surrounded by an ECAL and magnet. And then most downstream, and the one that doesn't move off axis, the SAND detector, which is a 3D plastic scintillator target surrounded by trackers, an ECAL and magnets. So now I'll go through each of those individually. So first, ND-LAR. This is a 50 to 60 ton fiducial mass liquid argon TPC. That large fiducial mass means that you get a large event sample, and the liquid argon TPC technology means that it's the same nucleus and the same technology as the FAR detector. So that's really good for that transferring measurements to the FAR detector part of the requirements. And this large event sample really helps with all of the other requirements. The differences to the FAR detector, though, are in the particular implementation of the detector. So it's a modular design. You can see some of these modules sort of in this cutaway here, and it has pixelated charge readout. So this makes it much more suitable for the high rate environment than the wire-based readout that we have at the FAR detector. And the modular design means that you can localize the light signals to really get independent T0 information in each module. One particularly nice feature of having a large event sample at the near detector is that you can do a measurement of the flux from neutrino scattering off electrons rather than the more typical neutrino nucleus scattering. We expect about 8,300 events per year in this process. And as you can see from the Feynman diagram down here, this is a QCD-free process. So that gives us a much lower uncertainty on the flux from this measurement than from a usual flux measurement. Next downstream is ND-GAR, the gaseous argon detector. It has a 1 ton fiducial mass gas target TPC surrounded by electromagnetic calorimeters and a superconducting magnet. The first function of ND-GAR is that not all of the muons created in ND-LAR are contained in the liquid argon. And that means you need a spectrometer detector downstream in order to be able to measure those muons. So ND-GAR fulfills this function. But the other really nice feature of ND-GAR is that gas targets have much lower energy thresholds than liquid targets. You can see this from the plot on the right-hand side here. This vertical line in solid is the gaseous argon proton kinetic energy threshold, whereas the dashed solid line, the dashed vertical line is the liquid argon proton kinetic energy threshold. What you can see is models that have very different shape in the gaseous argon region have very similar shape in the liquid argon region, but still quite different normalizations. And this means that we have to add extra uncertainties to avoid biases that would be present if we just assumed one of these models without taking into account this uncertainty. But if we have gaseous argon, we can just say which one of these models is correct and not have to add such large uncertainties. Being able to distinguish between these models is also key. Hadronic final states that contribute differently to the visible energy in a liquid argon detector, like final states with different numbers of pions. In a gaseous argon detector, we can see how many of each of those final states are present and really pin down those effects. Now I've taken you through the 2 detectors that move off axis. I'm going to go into a bit more detail about why we do that, enabling ND-LAR and ND-GAR to move perpendicular to the beam axis. And this is really because the on-axis flux shown in black here is very different to the off-axis flux. As you go more off-axis, you get a more peaked beam at lower energies. So by sort of moving in this direction, we can really sort of sample these different fluxes. And that allows an isolation of the flux, cross-section, and detector effects on rate, as I mentioned earlier. But it also enables a really cool feature of the detector, which is that you can take these different fluxes and make linear combinations of them to make almost whatever flux that you want. So here, this is an example of making Gaussian fluxes by combining all of these different bytes that you take out of the flux spectrum. And you can even go as far as to trying to replicate your FAR detector flux. So you can see in blue the near detector linear combinations overlaid in black on the flux that we expect at the FAR detector for a particular value oscillation parameters. The last element of the near detector conceptual design is SAND. So as I said before, it's necessary to have a fixed beam monitor to measure the beam's time stability. This is a key lesson from previous experiments. So the neutrino production targets that people have seen in the past occasionally fail And you really need to be able to pin down the time at which that happened, especially if it's a partial failure where it still keeps working. So this constant on-axis time-dependent measurement is a really key part of the experimental program. And because we're a wideband beam, it's also necessary to have a full wideband spectral measurement so that you can work out if the flux has sort of shifted in in energy space rather than just the total number of events. The 3D segmented plastic scintillator target surrounded by a low density tracker and incl serves this purpose very well with SAND. One thing I should mention is that in this particular detector, the tracker design is still to be finalized. So in summary, I've taken you through the DUNE near detector reference design, focusing on how it achieves the oscillation physics goals of DUNE. That reference design has 3 components plus the DUNE prism off-axis measurement technique that gives the ability to constrain all of the non-oscillation components that are necessary to make a spectrum prediction at the far detector without bias. So we have ND-LAR, an on-axis high statistic, a detector that can move off-axis, which is high statistics with the same technology as the far detector. ND-GAR, which is a low threshold magnetized detector for spectrometry and powerful cross-section constraints, and the SAND detector, which is an on-axis spectrometer beam monitor. Thank you very much.
Thanks very much, Patrick. Questions for Patrick? I don't see any, so maybe I can ask one. So Patrick, given you're from my institute, I'm going to ask you an evil question.
Thank you.
How competitive, is this monitoring that you've talked about with HyperK's plans in this area?
So one of the really nice things about DUNE is that we're starting the experiment from scratch, so we can really design the monitoring system from scratch. I think it's obvious that there's a lot of complementarity between the 2 experiments. So both experiments are looking at these prism technology detectors where you move off axis. One thing I'd like to focus on that's unique about the DUNE facility is the ND-GAR detector with its low energy threshold measurements. This will kind of really be the only detector that can make these very, very low hadron kinetic energy measurements in this neutrino beam energy range. So that's an area that gives us some sort of unique ability. And then also just sort of rather than focusing on competition, focusing on how it's a different beam that we have at DUNE. It's a wideband beam, and that necessitates making some slightly different choices. So with SAND having a sort of full spectral measurement, rather than, I believe HyperK are planning to reuse the Ingrid detector that T2K currently uses, which is more of a sort of a number of events based method, because HyperK has a much more peaked beam structure. So I hope that answers the question a bit without making anything too politically incorrect.
That was very diplomatic, Patrick. Thank you. Okay, thanks to Patrick again. And I think we should probably move on. So where are we? We are next going to the outer detector system for HyperK by Stephane. I hope I'm pronouncing that not too badly. Stephane.
Perfect. Hi, how are you?
Yeah, I'm well, thank you. I hope I didn't make a mess of your name.
You didn't.
Okay, very good. So please go ahead. I should hear you well. Please go ahead and start when you're ready.
Thank you very much. Thank you for this opportunity to present the Outer Detector system at HyperK on behalf of the collaboration. So first, greetings from California. It's 2:56 a.m. in the morning right now. So please, I hope you will forgive the pace of my voice at this late hour. So moving on, so Takuya-san and Gianfranca already introduced very well the detector. So I will move on maybe more about what's interesting for us in the OD. So I'm going to do here a bit of physics and talk about how it's important in terms of like measuring the mass hierarchy using atmospheric neutrinos. So to do that, normally, if you just look at the oscillation probability in void, so your electric neutrino appearance and ionic neutrino disappearance are function only on the sign square. So you don't have actually like a dependency sign of the mass square splitting. But if you add matter, your neutrino and antineutrino will have some enhancement or a suppression resonance because of actually the MSW effects. And if you have like this gamma term that you can add in the equation, you do have this like effect now when you have a dependency directly on the mass hierarchy. So how can you do that using like atmospheric neutrino? Then you can see here like a very crude sketch of ionic neutrino being produced here, having resonated by going through the Earth and then detected the HyperK over there. So this side is to show there is two actually key things you want to look at. So to first detect appearance of neutrino into a muonic neutrino atmospheric beam, kind of, and then to focus on the energy of relevance, which is here around the 2 to 10 GeV scale. When you can see here, in the case of neutrino, you have this appearance, this resonance over here, and here you have this disappearance of anti-neutrino, so this suppression. So then how can we move forward to increase maybe this mass hierarchy sensitivity? So the first thing that an experimentalist would thought is you want to increase the fiducial value of the detector. If you have like more statistics, more events, you can have like a better sensitivity. So how we can do that, for example, by improving the event selection. So right now in any like atmospheric analysis provided by Super K or the future Hyper K, you usually classify your event into different categories: fully contained event, which are fully contained inside the inner detector; partially contained, we can be in different segments; and upward going muons. And remember, it's important because the topology of our event, we want to see muons coming from the other side of the Earth, so they have to be like upward going, right? So remember this key point, we want to see like this electron appearance from the electron neutrinos. So then we have to veto cosmic muons quite efficiently. We have to improve the purity of this fully contained chamber, and also to better identify these upgoing muons. And also, this is a bit more of a niche thing, but what you can do as well is to be able to improve the selection, the separation of the stopping muon into different segments. So this is a key factor at this actually kind of energy, because you do have of these stopping muons a lot. So if you can, for example, tag better your partially contained event, if you have a stronger resolution on the entry and exit point, for example, of muons coming from outside of the detector, that's really important. And you can also increase the rejection capability. Also, another thing which would be nice is to use different segment as calorimetry. If you're able to more track your muon inside your detector in different segments, you would be also more able to reconstruct the energy more accurately. So this is why we proposed this kind of improved design, of the auto detector. So it's built using 30.3K of 3-inch PMT facing outwards. This corresponds to roughly 0.3% of photo coverage of the total OD area. You can see here a sketch of Hyper K you've seen before, but here is a sketch more in detail when you can see the panels here, which are the structure which is going to support the PMTs. Facing inward in the detector, so this like big bulb over there, and the little red dot are the outer detector PMT looking forward. This is an improvement, and this is an original design. This is a design compared to the original one from Super K, which used more sparse PMT, roughly like 1% of 8-inch PMT. But we do think, and we try to demonstrate that even though we reduce the photo coverage, we can gain with several techniques back the light we're going to miss, and also we're going to be able to have a more performant system. So, okay, that's the main point, right? How do we compare different setups? So when you think about different requirements and improvement that you have to do for your experiment, you have to think about your detector as mainly a veto for background particles. So it's a veto counter kind of experiment. You have like a set of PMTs and you want to trigger to be sure that you have a certain heat cluster above threshold. And you use the information in DOD in two ways. So the number of photoelectrons you collected will direct directly to the energy loss in DOD, so the energy of your particle, and the number of PMT hits basically is the energy loss as well, very related, but also the spatial resolution, right? The topology of the events. And of course, we build our design based on a Super K experiment, but we are able to like have these 3 key points that we extract to be able to design an improved detector. So one is to increase the number of PMTs. We think that actually the number of PMT linearly increase the amount of information compared to just increasing the photo coverage. And also, as any like good experiment based on light, you want to have a good light collection with the detector. And as Takuya-san as well explained a bit earlier, you want to have the lowest dark rate possible on your PMTs. So a few words on the dark rate actually. So here I want to show already how it's interesting to maybe move to a different system. If we use a simple cut, for example, that it's used right now in the Super K analysis for partially contained events, if you look at the number of it in DOD, this defines a window, and you can try to understand how many dark counts you have in this window. And just by moving from a system with 8-inch PMT, so remember you have at least twice less 8-inch PMT, but you have 10 times more dark rate, for example, from the typical 3-inch PMT that Gianfranca talked about, you can reduce by a factor 5 actually between the expected dark count inside an 8-inch OD system using a 3-inch OD system for the same photo coverage. So this is already interesting, and it doesn't match our requirement, but we want to keep a low dark rate for our OD system. This is the different candidates that Gianfranca as well talk about for the MPMT, but we use as well those candidates for the Outer Detector from Hamamatsu, HLC, and ET Electronics. We presented and we have a paper already with the latest dark rate measurements and the results using this PMT. So I encourage you to follow the link if you're interested. However, I will focus a bit more on our system in this presentation and how we can actually use wavelength shifting plates to be able to collect extra light inside the OD. Here, this is how it works. So this is a pictures coming from Super K because the system which is already in place over there. So basically you have this big square of transparent plastic, which is usually PVT, something with an index of refraction of 1.5, and it's covering on the side of the PMT as the PMT is inserted, and you have actually the conductivity between the plates and the PMT on the edges that you can see over there. And here, for example, we light it up with a UV light, and we can see the light being guided in the plastic towards the PMT. And doing very simple like geometrical optic, we can actually try to understand how much more light we're gonna collect with this system. You can compute what is the critical angle, so the angle of light trapped inside the plastic. And you can also see that collection probability, which is the ratio of solid angles, is cosinus of this critical angle, and this gives you roughly like that half of the light which has been captured inside the water will be transmitted to the PMT. So that's really interesting. Here, so that was a theory, and that's started to do some measurements. So we have trying to we have several candidates for the wavelength shifting plate that we are like measuring. So there is a free company, LGen, which have existing prototypes already that we have bought and we are characterizing. Kurarai, which is usually doing fibers, but they also tailored some prototype for us that we can maybe use in the OD. And there is also this company called LabLogic, which is based in the UK, which has not a prototype, but we are working closely with them to be able to get new samples. Here you can see, so the name of the game here, you have the absorption of your wavelength shifting plate and the emission. You want to absorb as much photons in the UV region, because this is where your Cherenkov spectrum will be the most prominent, and you want to re-emit actually as the maximum of the quantum efficiency of the PMT, which is represented over there. So as you can see here, we do have like very like good candidates because we both match the emission, the absorption and the emission that we expect. And then the only thing you can play off is with the refractive indices of the different plastic, right? Because the higher indices you have, the more light you're going to trap inside your plastic. We have a setup where we can do measure the property of the wavelength shifting plate. This is done at the University of Edinburgh. They have this black box when basically you can see here there is a PMT, a fringe PMT here, which is inserted on the square 24 by 24 centimeter plate. And they use an LED, which they can flash on the PMT and all around, and they can see, we try to calculate what we call the efficiency, which you can see here, which is basically how much more light we can collect by adding the wavelength shifting plate in this system. And we move radially the LED from the PMT top, and we can see how much light we can collect. So we have this measurement going on, and we also have in parallel a simulation model of the expected wavelength shifting plate size. So this is what the side mismatch from what I said before, but this is what we can expect to maybe put inside the hyper-KOD. So this is the results. So we have like different things happening here. So this is a plot of the result. The data points are here. We have a model which just takes into account the reflections inside the plate and the light attenuation, and they fit already quite well the data point. The black points, we are using cladding all around the plate. So we can, as you can see here, enhance by a factor 2. When those data points here, we don't use any cladding. So that's also very interesting. And here you can see our simulation results. And so this is the PMT size. And this is as you're moving forward, we can see that we can replicate quite well the data. So that's really good. So as I mentioned, so we have this like cladding, which gives you a very important factor. But the most interesting thing is by using this system with a 50 centimeter square plate times half an inch of the size, you can almost have a 2.6 light increase. So compared to before, if you remember, we have 0.3% coverage in the OD compared to the previous 1% coverage from the original Super K design, but we can almost catch back thanks to this system. So in summary, the HyperKOD will be designed with a large array of small PMTs in order to improve the light collection, the spatial resolution, and we'll be able to veto and select more efficiently and categorize the topology of different events. There is also a lot of redundancy, which is quite interesting with this system if you have like failures of PMT. And we do have as well like a large set of PMT and plates we are on the test. And here's just a little word because it's also help us, the system, to build up how we're gonna implement the results into simulation. So we do have a full simulation already of HyperK, which is building this package called WC Sim. We have also the OD inside, and we're gonna develop this two-stage. We're gonna use this ad hoc simulation and results to have this light collection enhancement put inside the simulation. Thank you very much.
Thanks very much. Very nicely on time. Questions for Stephane? Okay, I don't see any immediately. Excuse my ignorance, but this factor 2.6 gain you talked about at the end, is that somehow in your plan? Is it in your, how to say, in your planning in terms of the end sensitivity you get, or this is just all, you know, one of the range of ways in which one will cover having the larger photon space, having the larger spacing between the detectors?
So it's the good thing about this factor, it does match what we can expect from before, because this system was used before in IMB and then in Super K. And if we just already scale, for example, using this critical angle we computed here, and then we can and then we just like scale with the area of the system, because we go from SK smaller plate, bigger PMT to the other way around. And it's quite good that we can actually kind of catch back the light, the photo coverage you're going to lose, because some people can be scared that you're going to try to build an optical detector, but you want to reduce the photo coverage. And we say, well, no, we want to put more PMTs, because before with more PMTs, we have more information. We can maybe use this to have like better resolution on topology. And however, with this system as well, it's a very cheap way to kind of catch back the light we lose. And for example, in SK, because this is our reference, they do have a very efficient system using this 1% coverage of the OD. So for us, it's quite good to say that we can have more PMT, so more redundancy and more of this information, and keep the same photo coverage.
Okay, so but this is kind of part of your default sensitivity planning, as it were. So the factor you described is already somehow in your curves of how sensitive you think your experiment will be.
Right now, it's true, because we focus here on the hardware. So this was the first step to be able to have set a design and then move on. But then we need to see how we can this put in the analysis and we can improve. So this is the second stage, but it's not ready at this time indeed.
Okay. All right. Thank you.
Thanks.
Okay, good. Thanks a lot again. And let's move on. If I can find the right window. And I believe we're now moving to Pierre Auger. Radio detector upgrade, and that's Sibrand. Sibrand, are you there? Oh, I can see you started sharing screen. I don't hear you yet. So I see the screen, but I don't hear anything.
Yeah, sorry about that. Okay, so when you touch the screen, it puts the mute button somewhere else.
Okay, no problem. So I hear you well now. Please go ahead.
Okay. The Pierre Auger Observatory is a 3,000 square kilometer ultra-high energy cosmic ray detector that's situated in the Pampa Amarilla in Argentina. And the energy range of interest of the cosmic rays that we want to detect is for particles of about 1 eeV or higher, so extremely high energy. And originally the Auger observatory consisted of a surface detector array of 1.5 kilometers spaced water Cherenkov tanks and 4 6-station fluorescence detectors that look over the area for the faint light emission of the showers in the air, in the atmosphere. And the observatory is now being upgraded to Auger Prime with new layers of detection that should improve or make much better the particle ID of the cosmic rays. The take-home message of this talk is that a detection technique of ultra-high energy cosmic rays using radio frequency emission of the air showers has been developed over the last 2 decades, and that is now mature enough to be applied on full scale of the 3,000 square kilometer Pierre Auger Observatory, and we are actually constructing this new detector layer. So, let me switch on the pointer. the reason for more and better detection of ultra-high energy particles from the cosmos is that we see them, we detected them, but we still don't know where they come from or how they have been produced, which must be from exciting physics because they're extremely high energy. And also there must be lots of information in there for astronomy. What we can study is their interaction with the nuclei in the atmosphere, but this is hampered by the fact that the projectile particle type is not yet known. So the problem is that particle type that is badly or not measured at ultra-high energies, and certainly not on an event-to-event basis. And that hampers the tracking back of the particles from their arrival direction to the sources, and also the interpretation of their interactions at ultra-high energy. The measured spectrum, which is on the large left-hand side panel in this slide, has been measured, the energy spectrum has been measured to very reasonable accuracy, with a spectacular drop at the end. You have to mind that the plot is the energy spectrum multiplied by e to the power 3 or so. And on the low-hand side of the energy range, these are mostly cosmic rays from galactic origin, and at the high end, they are from extragalactic origin, which is the range of interest for this experiment. However, at that part, we cannot measure at this moment the particle type. And the idea of the upgrade is that we would be able to measure the particle type, which would then give the composition components, but also an event-to-event composition, which would allow all of these, solving all of these mysteries that I just mentioned. There are two methods basically to measure the composition. One is the penetration depth into the atmosphere, which is called Xmax, which is a measure for the cross-section of the particle. And clearly the heavier the particle, the bigger the cross-section. And the other one is the muon yield, so the relative number of muons in the event, where again more muons point to a heavier composition, to heavier particles. So these are the two methods. The problem with the muon yield is actually that it is not very well predicted from the LHC range upward to our range of energies. And there's a discrepancy between the Monte Carlo simulations and the measured rates. So how do we do this? So the first part is, let's see where my pointer is that we place a scintillator detector on top of the water Cherenkov tanks. And this has been dealt with in a talk by Gabriele Cataldi in the Operations Performance and Upgrade of the Present Detector session last Tuesday. And the idea is that there is a different response of the electromagnetic component of the shower and the muons in the water tank and in the scintillator. And from that you can unfold the electron component and the muon component, which gives you this composition separation. The other way, which is the subject of this talk, is to put an antenna on top of the water Cherenkov tanks, which is indicated here with the hoops. There are two hoops. It's called a Sella antenna, and they detect the radio frequency emission from the showers. That is a measure of the electromagnetic energy in the shower. At the same time, the water tank, which has a volume, so it's not a surface detector, but it has a volume, it detects the tail of the muons in the shower. And then again, you have the total electromagnetic component of the shower and the number of muons, and you can do a separation. The antenna is operating in the 30 to 80 megahertz frequency. It's being read out by a separate electronics board, which also digitizes and pre-processes the signal, but then it is merged into the data acquisition that already exists for the SSD tanks. And in that way, we could actually use all of the already existing infrastructure and make this detector relatively cheaply. The two methods complement each other because one is for vertical showers and one is for horizontal showers, which really extends the range of the exposure. even up to the northern hemisphere, because we really look at the horizon. And so that's the complementary part. So we get just more events with particle ID. And the other part is that in the overlap region, there's also an overlap region. You can calibrate the different methods of separating electron and muon components with different detectors. The number of extra events that we expect from this radio detector is of the orders of tens of thousands, and this is in this field actually a large number. So apart from the normal cosmic rays, which are supposed to be charged nuclei, the radio detector will also enhance the capabilities of looking at ultra-high energy neutrals in inclined showers, notably neutrinos and photons, where on the left panel is plotted theoretical predictions for the flux of neutrinos, which are the shaded bands, and superimposed present limits and future limits. No, actually only present limits. And then you see that the present limits actually sort of start touching on the predicted area where we should find these particles at ultra-high energy. So 10 to the 18 eV is 1 extra electron volt. And we should be able to improve this by an order of magnitude. So we should dive deep into the theoretically predicted area and either discover neutrinos or not. And if we don't discover them, that will have serious implications for the theoretical models. The same is true for photons, which are also expected to emerge. Where again, okay, the present limits sort of start touching on the expected range of these ultra-high energy photons. And by improving an order of magnitude, we again dive deep into the expected area, and we will be able to either discover them or say much about the theoretical models. So zooming in on the radio detection technique itself, a lot of it has been tested over the past 2 decades in several experiments, and notably in the AERA experiment, the Auger Engineering Radio Array, which instead of covering the whole area of all the 1660 tanks, covered a small area of about 10%, well, less than 10% of the surface, but 10% of the detectors, about 160 detectors, with all sorts of different spacings, trying different antennas, trying different electronics and DAQ, etc. And there we gained a lot of experience and we are sure that we are ready to operate a detector at a much larger scale. So the principle of the radio detection is that the shower emits 2 types of electromagnetic radiation. One is called geomagnetic, is the bending of the charged particles, the electromagnetic charged particles in the Earth magnetic field. And the other one is a charge separation, where the negative charges collect in the shower front and the positive ions stay behind. And these 2 induced pulses, they interfere. And there's also the effect of Cherenkov interference because of the finite index of refraction of the atmosphere. And that makes that the detected signal is a rather complicated pattern, where in this panel, with the blue shaded outside and the red inside, you can see the footprint of an event. And you see that it is not actually symmetric around the impact point, which is somewhere where my pointer is now at all. And also if you project it onto a radial axis, then you see that there's a big mass of points. But actually we can now quite well predict the details of this footprint. And from the details of this footprint, we can reconstruct the energy, well, and from the time we can reconstruct the direction, but we can also reconstruct the composition from the details of this footprint. What you can also see on the absolute range is that typically such a shower is about 100 to 200 meters in diameter of where you can actually detect it. This is for a vertical shower. For horizontal showers, the footprint gets much bigger, which is shown here. So this is a vertical shower on the right, which is a small spot, and then at 30 degrees inclination or 30 degrees zenith, it's already getting an ellipse. At 50, it's getting a bigger ellipse, and at 75 degrees, it's actually a huge ellipse. And then you see that the scale here is actually in sort of kilometers, and the spacing of the water Cherenkov tanks, which is a 1.5 kilometer spacing, is actually quite well adapted to detecting that sort of footprint. We've tested that in AERA, and we also seen already more than 500 inclined showers. And this is one event where you see that all the colored crosses are stations that are hit by this event in the radio. The green points are the surface detector stations that have been hit and that are used to check the reconstruction. But then if you go to a 1.5 kilometer spacing, then you see that even then, in this case, you would have hit 5 of these radio stations and that the event is not even in the fiducial. So if you would extrapolate it to a larger array, you would certainly have like 10 stations hit, which would give excellent capability of reconstructing the event.
You've got about 2.
Yes, this is my last slide. So, well, the penultimate. No, this is the last slide, sorry. So, the status is that the mechanical design is complete and tested, and there are lab tests and the tests in the field. The electronics design is nearly complete. We're still optimizing gain and noise performance to be able to calibrate on the galactic background. There are already 10 prototypes in the field for about 8 months, of which 7 are being read out. And from this, I can show you an event, which is appearing on the left-hand side. Actually, these are 2 events. The first event is one at a zenith angle of 46 or 47 degrees. Both events are around 4 to 5 EeV. And the lower panel is an event at 72 degrees. So that's a clearly inclined shower, and this is closer to vertical. If you look at the left-hand side panels on the right-hand side of these plots, then you see here where the cursor is, the signals from the PMTs in the water Cherenkov tank. There's the scintillating detector, which is the thin scintillating detector on top, which also has a signal, which coincides for this event. And then there's the radio signal. Never mind the time coincidence, we're still working on that. Well, actually that has been fixed, but not in this picture. And you see that all of the detectors fire. So this is an event in the overlap region. And then the lower event is an horizontal event. And there you see that there's no signal in the scintillator detector because the scintillator detector is very thin. And so it has no cross-section for this shower. But you see the event in the radio detector. And you see the promise of the extended inclination range. So we are nearing the design finishing, and we hope to start production by the end of this year. The deployment will be in 2021, and then there will be another decade of measurements to be done for the ultimate result. So do as the radio detector does, stay tuned.
Thanks very much. Good, questions?
Yeah, can I have a question?
Please go ahead.
Yes, since you are in the Pampas, I assume they are quite radio quiet. What is your most important source of backgrounds? Is it amateur satellites? And another question is, since you do 32 to 80 megahertz and you have antennas with quite large angular acceptance, did you consider doing a phased array technique to better get the point of where the shower is coming?
Yeah, so the answer to the first question is that although we are on the Pampas, there's actually quite a bit of human-made noise. So that's really fighting that. It's not that radio quiet as you would assume. Of course, it's not as bad as in the city, but it's not really radio quiet, but it is manageable. In fact, for this array, the triggering will be primarily on the water Cherenkov tanks. So it will operate in slave mode. And that makes that the background is sustainable, okay, because you're not drowned in data. Then about the phased array, this is certainly a possibility. However, the array, of course, operates a little bit differently in that all the stations are autonomous and read out each of them at their own time. We are investigating using the phasing, the relative phasing, but for that, of course, you have to have a relative timing of the stations, which is really good. So, and GPS alone is not good enough, probably. So we're investigating things with beacons to make a relative timing of about a nanosecond or so, or a few nanoseconds between stations. And that should also allow this to be used as a phased array. But that can only be done offline, so we cannot have a phased array trigger, for example.
Okay, thank you.
Okay, so I think we better move on. Although I understand the schedule, we're moving back to your second talk.
Yes. Okay, so this is nearly a natural continuation. This is about the giant radio array for neutrino detection. This is an array that should be large enough to detect ultra-high energy cosmic neutrinos with an energy above an EeV for any, say, standard scenario of the theory. And it turns out that one would need an array of about 200,000 square kilometers to do that. Now, of course, this is a big challenge. Okay, this 200,000 square kilometers is about 3 times the Czech Republic area. And therefore, we have to follow a staged approach where we develop such an array, and we can also deploy it in stages. And so that is what this will be about. What is the idea of the detection of neutrinos? Let me switch again to the laser pointer. Oh. The idea is that at energies at which we are interested, okay, which is around an EeV, the cross-section of neutrinos, which rises with energy, actually gets appreciable with the Earth. And so if neutrinos go through mountains or are Earth skimming, they can interact with the Earth with a reasonable probability. So the probability is plotted here in this figure on the left lower corner. And you see probabilities going up to like a 10% level interaction probability for a neutrino to be interacting and for the charge track to emerge in a charge current interaction. Now, of course, there are 3 types of neutrinos. If an electron neutrino interacts in a mountain or in the Earth, what happens with the electron is that it will pretty quickly start to form a shower, and it has little opportunity to escape from the Earth or from the mountain. And so there's also difficulty to detect it. For muons, this is different. Of course, that the muon will escape, but it will not generate much signal in the atmosphere. So that will also be very hard to detect. So the nice thing is the tau neutrinos, which if they interact, they make a tau, if they have a charge current interaction. And then the tau, because of its lifetime, actually flies about, for this Lorentz contraction factor, about 50 kilometers before it decays hadronically. And then when it decays hadronically, it more or less immediately makes a shower in the atmosphere. The shower in the atmosphere develops. And from this shower in the atmosphere, also by the mechanism that I just explained, you emit radio frequency radiation, which can be detected. And this radio frequency radiation is traveling unimpeded through the atmosphere, so you can detect it at much larger ranges than the shower actually has died out. So this is the detection principle. So why would we want to detect cosmic neutrinos? Now, of course, they are the guys that point back to their sources. So you could think of detecting neutrinos from sources. What do you expect for a yield? Now, we already have measurements from IceCube, but of course, they are probably in the region of galactic sources. And you could extrapolate it a little bit to higher energies, and there you could have some expectation of direct neutrino production in sources. The other source of neutrinos is in the interaction of cosmic rays with the cosmic microwave background, or even the infrared background from stars, where they will produce pions, and these pions can decay into muon neutrinos, and the muons decay into muon neutrinos and electron neutrinos again. So there also you get a bunch of neutrinos. Now, most of these neutrinos will actually be muon neutrinos at the point of production. But because they are produced far away, they will oscillate into all sorts of neutrinos, and you expect sort of 1/3 to emerge as tau neutrinos, which is then the principle of detection. Again, in this figure, the range of expectations is given in the gray bands. There are some limits which are given here, which are above these gray bands, so we do not really expect something to be detected yet. And then the expectations for the proposed experiment, GRAND, are plotted here in the orange lines for different exposures and in a differential and an integrated way. And there you see that we go into, for the integrated way, we go into the expected range of all sorts of reasonable models up to the bottom. So we should detect all sorts of, well, if the neutrinos behave according to a reasonable model, we should be able to detect them. Yeah, this is what I said. You can extrapolate sort of the IceCube flux, and then we should also be in the range of detecting those from the sources directly. In addition to neutrino detection, you can of course, and establishing their sources, you can also use them for neutrino physics. You can do cross-section measurements at these high energies, etc. Okay, by looking at the ranging in the mountain, etc. In addition to these neutrinos, of course, also there are these ultra high energy photons, which will also be able to detect with such a radio detector. And of course, a large number of cosmic rays that will also be detected. Now, of course, the photons and the cosmic rays will be backgrounds to the neutrinos, but looking at very inclined showers that come from a mountain or from Earth skimming, you don't expect photons or cosmic rays, you only expect neutrinos, so they are actually quite well separable. In addition, in addition to the following up on the question, this array is, we're trying to make this a little bit better phased radio array also, to be used for purely radio astronomy type of things, but that's not the topic of today. So the performance, I already shown this plot, okay, so where we expect to really be able to see tau neutrinos, and that's why we need this 200,000 square kilometers. These studies are based on extensive Monte Carlo simulations, which have been documented in a white paper, of which the reference is at the bottom of this page. Then, then for photons, we also see that we go deep into the area where you expect these photons from all sorts of reasonable processes. So you should be able to also see these photons. And if we don't see them, something funny is going on. And for cosmic rays, we know that we will see them, and we will see them with 1 or 2 orders of magnitude more data than will ever be collected by Auger or let alone TA. Because we are looking at the horizon, I think very much inclined showers, the exposure is a little bit peculiar, and you get these rings, and just above you and below you, you have sort of big black spots. Now, of course, the Earth is rotating, so you cover, if you integrate it over time, about 80% of the sky. But on any particular time, you only cover sort of a circular wedge-shaped part. So this makes that you may want to do this not in one location, but to distribute the detector over 10 to 20 what we call hotspots. And so we have 10 or 20 different sites over the Earth, and together they have more or less a continuous overlap with the complete sky. That is the idea. And also that allows for a staged approach, because then if you have one of these hotspots of about 10,000 square kilometers, you already have a yield, which is given here, the exposure, that is so big that you can do very sensible science already with the first hotspot. So this is the roadmap for GRANT. Already started was a small array of 35 radio antennas for testing in the sort of in the Chinese mountains, which was quite successful, and also testing the idea of self-trigger, triggering on the radio signal itself. And this is one is able to do that because that is in an extremely radio quiet area, unlike the Auger area. And at present, we're working on Grand Proto 300. This is a 300 antenna array over 300 square kilometers. From that on, okay, we hope to make the jump to the array with 10,000 antennas, which would be the first hotspot. The status of this Grand Proto 300 is that we have a station design where we have the antenna on top of the pole. There's a long pole to make sure that there's not so much radio interference of the box beneath the pole, and also not so much reflections from the ground plane. Halfway the pole, there's a communication antenna for wireless communication. All these stations are autonomous. So below there is a box which has a solar panel to harvest the power, and has the electronics and the battery inside. And then very much below is sort of a dead weight to make that it's stable on the ground and easy to deploy. The present design is optimized for easy accessibility and testing, and being able to alter things. The final design can be much more sort of less flexible, and should also be much cheaper. A key element is the radio antenna, which should be optimized for horizontal showers, which is not an easy thing. Okay, vertical showers is much easier. It's a design with 2 polarizations in the horizontal direction and 1 polarization in the vertical direction. So it measures all 3 polarizations. And a lot of testing of the patterns of the acceptance of the signal, what is called the vector effective length. This has been going on. The range of interest is from about 50 to 200 megahertz. And then, of course, one needs the electronics. So there, a lot of the design has been completed. There's a low noise amplifier after the antenna, which is mounted straight on the pole, straight at the antenna. Then the amplified signal is going into a filter, which does a frequency filter, an analog frequency filter. Then there's the ADC, and then there is a board with a lot of digital electronics, which treats the signal and also does the housekeeping. And actually, as you can see, we have this board in hand. And it has been tested, and the final adaptations are being made. So that brings me to the end of the grant talk. So the grant status, this is about a huge ground-based radio array, is unprecedented for ultra-high energy neutrino detection, but also gamma detection, cosmic ray observatory. It is actually impressively versatile in astroparticle and particle physics. Being able to address lots of things. There's a no-lose theorem for ultra-high energy tau neutrinos. If we don't see them there, we know that something really weird is going on. And there's a roadmap for staged approach, and we are at a point where we have a 300 antenna array being produced. We are actually a new and open and lively and growing collaboration, and I would welcome you if you have interest to join. Thank you.
Okay, thank you very much. I see there's already a question from Jakob, so please go ahead, Jakob.
Yeah, hi. So I have a question. So whether you have an estimate on the Xmax resolution that you can achieve for ultra energy cosmic rays?
Okay, for grant, the Xmax resolution, okay, we think we may also be able to do something about that, okay, but it's not so much the relevant thing. This will be very difficult in horizontal showers. So the thing they can do is, of course, you measure the electromagnetic component of the shower, and to do this type of particle ID, you would need also, at least for part of the array, particle detectors to be able to measure the muons in the tail of the shower to be able to do this type of particle ID. However, we are looking at seeing with this idea of phasing, we actually can get information out on Xmax, but these studies are just beginning.
Okay, thanks.
Maybe if I can have one more question.
Sure.
Or maybe an idea. Since you need some precise information for timing, and you are sensitive in the, I don't know, according to the dimension of antenna, let's say 100 megahertz range, cannot you use pulsars for synchronization?
Yeah, maybe. Well, but of course, no, because their signal would be much too low for these antennas to be able to see.
Even if you phase the array and move the location across the sky in a phased array, you have sensitivity, and if you do it,
no, but that's a catch-22, okay? Because you cannot have the phased array if you don't have the timing, okay? So that's why I was thinking, okay? So if you have to start at some point which is relatively far away from your from true phase, then it's hopeless to detect these pulsars.
Yes, but you have a very wide band, which means you can, at least to some extent, correlate fix
but also we can only be, given the approach to the data acquisition, we can only trigger station by station. We cannot trigger the whole array. We have no bandwidth to read out the whole array.
Okay, because if you did, you know where the pulsar is, you know the distances, and you can have the clock.
Yes.
But okay.
Yes. But it would probably be easier to set up a beacon somewhere, our own pulsar.
Yeah, probably. Thank you.
Okay, so thanks again for both talks, and let's move on. And Jakob, I know you're here if you've asked a question, so I believe you're next.
Okay, so can you see the screen?
I can, yeah, very good.
Okay, so
you are.
I'm going to talk about the Southern Whitefield Gamma Ray Observatory that we plan to build in South America, and it's going to be based on water Cherenkov detector units. And the abbreviation so far is the SWGO. Okay, I'm giving this talk on behalf of the SWGO collaboration. Let me start with a brief overview of the gamma ray astronomy, especially the detection techniques. So if you can detect the gamma rays up to 100 GeV directly with a detector on board of some satellites, as in case of the Fermi. However, if you want to detect gamma rays above 100 GeVs, you need to use some ground-based detection techniques. So whether you can build an array of particle detectors somewhere in the altitude between 4 and 5 kilometers above the sea level and sample secondary particles, or you can build Cherenkov telescopes at a level above 2 kilometers above the sea level and collect the Cherenkov light that is produced during the propagation of the secondary particles. So comparing these two ground-based detection techniques, so in case of the IICTs, which is the shortcut for the Imaging Earth Cherenkov telescopes, so you point the telescopes to a given direction with quite small field of view. However, you observe that region with very good energy and angular resolution. Still, you need to observe only during dark nights with low or with a good atmospheric conditions. So it means that you end up with a low duty cycle. However, you can go down to, let's say, tens of GeVs energy of gamma rays. In case of the arrays of particle detectors, then you can observe a wide field of the sky. So typically it's like 130 and solid angle, and you observe all the time. You don't care whether it's day or night. However, the energy threshold is higher than in case of IICTs. It's hundreds of GeV rather like 1 TeV. Anyway, you can observe one particular region in the sky for a long time, so you can collect high exposure and accurately determine background cases. So I'm showing here the plots of the, let's say, the most dominant experiments in the near future. So there is going to be built, or currently is being built, a CTA that is going to have two sides in the northern and also in the southern hemisphere. And there is this HL-LHC, which is the array of particle detectors built in Mexico, and LASSO, which is an experiment currently being built in China. And HL-LHC is using the water Cherenkov detectors, these water Cherenkov stations, these big ones, and LASSO is combining several detection techniques. Okay, looking at the geographic locations of the experiments, you can see here in the red in case of the Cherenkov telescopes. So both hemispheres are covered by these instruments. However, in case of arrays of particle detectors in blue, you can see that currently there is a missing such an array in the southern hemisphere. So the southern sky is not covered by this. And the SWGO should change this. Okay, so as you can see here by this orange rectangle, the locations of the proposed sites for the SWGO. So some motivations for, or why to go in south. So the main motivation is that we could observe then the galactic center and a significant part of the galactic plane with SWGO as it is indicated here. This dark region here is the region where HL-LHC is not able to see the sky, and SWGO would be able to do so. And also it's important that significant part of the Fermi bubbles would be observed as well. And here in the left, you can see first estimates how sensitivity to the Fermi bubbles in case of SWGO should improve with respect to HL-LHC with regards to Fermi bubbles. Okay. So another thing is that is important for such a wide field observatory is that it can provide triggers or alerts for the more precise Cherenkov telescopes, and especially in case of the gamma ray bursts. So you know these very extreme violent messengers from the universe, and However, the main thing is that most of the GRBs are currently escaping possible detection, because the best GRB trigger, the Swift bet experiment, is field of view at 1.4 steradian. Anyway, what is important is that last year, in 2019, first 3 GRBs of energy higher than 100 GeVs were observed. So such GRBs exist, and if you have observatory possible to detect showers of these energies, so you should be able to see those, and could in principle trigger the CTA for this, to have a more precise measurement of such transient events. Also, on the other hand, if you observe for a longer time, you can, and larger part of the sky, you can see some flares, for example, for AGNs, and yeah, some large-scale features like the Fermi bubbles, and also give a trigger to CTA, not in such a short time as necessary for the transient events. And also, last but not least, important motivation is the multi-messenger study, because of course you need to have some observatory possible to detect GRBs in the southern hemisphere in case of the coincidence with the gravitational waves or some neutrinos. Okay, so the SWGO collaboration was established last year, and now it's in its 3-year R&D phase, in which we are trying to find the best location for experiment and define the concept of our detector. So currently we are almost like 200 scientists of 44 institutions from 11 countries, and we benefit from the expertise of people from HL-LHC, Argo, Meiji, GAS, Auger, CTA, and others. Okay, so with regards to the core science cases that have been already defined, so I already told you about the short timescale phenomena, the GRBs and AGN flares. So then we also want to probe the flux of gamma ray sources at around 100 TeV in case of the galactic plane, or around or close to the CNA location, as we could then indirectly say something about the possibility to have pevatrons in our galaxy, or something about the acceleration of ultra-energy cosmic rays. Another important thing is to search for the pulsar wind nebulae in the galactic plane, which in principle could still be missing our knowledge, and these could be also in some sense responsible for the positron excess that is observed by AMS. It's important to fulfill the catalog of pulsar nebulae. And as we will be able to observe the galactic center and also the galactic halo, so we'll be able to put limits on the cross-section of the dark matter annihilation. And another important thing is that we aim to have a very good identification of primaries, not only gamma hadron separations, but also possibility to distinguish between protons and heavier primaries in case of the cosmic rays. So of course the cosmic ray composition and anisotropy studies are of one of the primary importance, and especially in the case of the joint analysis with LASSO experiment, for example, in the north. So then the full sky coverage could be provided. Another important thing is the diffuse emission of cosmic ray background in the galactic plane, which is also something that is not well studied yet, especially above 30 TeV. And of course, we'll do a survey for some new point sources that could still be out of detection so far, significant detection. Okay, so to do this, what do you need is to decrease the energy threshold as low as possible. So our goal is to reach 100 GeV for high quality reconstruction of gamma showers. And for that, we want to build our observatory high in the altitude, so above 4.4 kilometers, and improve our detection efficiency as much as possible. And the array should be large, in a sense of like 4 times the Hawk size to have a reasonable statistics at the highest energies. And of course, for all these goals, we also need to have a good angular and energy resolution. And as I told you, the identification of primaries. Okay, so what regards the consideration about the concept of the detector, so it will be based on the water Cherenkov detector. So there is a question what would be the final decision how to build it. So far we are considering like building a pond of water, like in case of the lasso, and this pond of water would be divided by several layers. So you have a segmented detector in there with muon tagging, for example, or you can consider that we could in principle build some or put some floating detectors in a natural lake behind the mountains, and yeah, use the detectors like that, and spare fundings for water transport and other difficulties. Or we can stick to a more conservative way, which would be tanks of water, like in the HL-LHC, something like that. But we are still thinking about the optimization of the dimensions, locations of the photosensors, whether there will be PMTs or silicon PMs, and whether the walls will be black or diffusive white, like Tyvek. Whether these tanks will be segmented, like in the bottom part, you can then take for muons. It would be important, or also to distribute the photosensors in a way that you could observe the direct light of muons and then also use it muon tagging as well. Anyway, whatever concept is chosen, so the layout should look like this. So there will be like high fill factor area inside with a radius like 150 meters. We plan to reach the fill factor like 80%. And surrounding this high fill factor area, there will be an outer array of a lower density that will help us to out-trigger the cosmic ray background in this case. What regards the candidate sites, so we end up with nine sites in Peru, Argentina, Bolivia, and in Chile. And as you can see here, the altitudes of the site are quite high, so it will be quite challenging, to build an experiment there. So we need to find out also very demanding engineering solutions for that, because water transport, manpower, maintenance, things like that. However, so far we haven't chosen sites, but we are going to install some dedicated environmental devices there and some prototypes to especially study the water freezing levels, so how often and how big such an effect would be on detection of water Cherenkov detectors. Some first estimates how well we could go with regards to the angular resolution on the left. SWGO is here in green and orange, is shown here, and on the right is this indicates of the sensitivity, which is a quantity that tells you how well are you able to significantly find gamma ray source. So the main thing is that we will go, of course, towards the Cherenkov telescopes with respect to the HL-LHC. So we will do improvement detection techniques, but most importantly, we want to go to this lower energies. Okay, so finally, at the end of the R&D phase, so let's say in 3 years from now, so we should have a selected site for which we will have to define and prove the technical concept, and of course, we will then provide precise estimation of SWGO performance and impact on the science cases that I showed you before. And so having SWGO in the south, LASSO experiment in the north, and together with Cherenkov telescopes of CTA in both hemispheres, so there will be a start of new gamma ray era covering almost the full sky. So, thank you for attention.
Thanks very much. Questions for Jakob? I don't see any. So I was curious about the kind of order of magnitude of capital cost for this project. If you
sorry about what?
What's the order of magnitude cost of this project?
So the target cost is like between 40 and 50 millions of euros.
Okay, very good. All right, so it's a pretty big scale thing.
Yeah, with respect to, yeah.
Okay.
Maybe
Very
I can have one more question.
Please go ahead.
Yeah, so now with this renewal of cosmic activities and SpaceX launching tens of thousands of satellites into orbit, would it affect your observation?
I don't think so. Or in what sense, you mean?
That you will have thousands of light sources moving in the sky.
Yeah, but we are observing, showers. So
you have a very, very sharp peak of the signal, and you have
yeah, we are
wavelength
detecting
filter.
particles reaching the ground. So there is some light
For the
source.
triggers, okay. Yeah, okay. But in the optical range, this won't pose a problem. For the Cherenkovs, I mean.
Sorry?
For the Cherenkov radiation, it won't pose a problem.
No.
Okay.
It could be some small problem for the Cherenkov telescopes in some case, but still the flashes that you observe are very fast, so it's typically
Very fast, so you can see them very clearly from the background. Okay, thank you.
Yeah, should not affect, to my knowledge.
Okay, so thanks very much to all the speakers in the session. And I believe that brings the session to an end. So maybe if it's not too silly, we can unmute and applaud all the speakers, given we didn't manage that as we went through. Okay, I'm going to start.
Yep. Okay.
So thanks, everyone. Thanks a lot.
Thank you. So I will stop the recording. Is the ZTA online?
Yes, I am.
Yes, okay, perfect. So I will stop recording. Now, what should I do? Just keep it.
Yes, you should keep it, and then the organizers will tell you if everything is okay.
Okay, so I can close this Zoom system. Okay.
Thanks very much for your help.
Thank you.
From my side. Thanks a lot.
Yeah, you're welcome.
Take care.
Thank you and bye.